This is the video for the Unit 6 test review guide. And number 1 asks you to use the vertical line test to decide if each of these graphs is a function or not, and you're just going to write yes or no. And in the first one, it's going to be no, because I could draw a vertical line in several places where it would touch the graph more than once. In the second graph here, there's technically asymptotes. They're hard to, not always easy to tell because, again, an asymptote is infinitely narrow and it's hard to see on a graph when there's part of the graph is up at the top of the asymptote and part of the graph is down at the bottom of the asymptote. But this graph is the graph of a rational function, and therefore it does pass the vertical line test, and yes, it's a function. Now in this graph, the third graph here, it fails the vertical line test at these two weird shaped closed circles. I don't know where I got that from, but this is not a function because of there being two x values at x equals, or two y values at x equals 2. And again, here, there are several places where I could draw a vertical line and touch the graph more than once. And so this is also going to be no. This next graph passes the vertical line test, so yes. And I guess that's it. 5 graphs, no, yes, no, no, yes. Now, in number 2, you will be asked to substitute. I guess I didn't put that in the answer or in the directions, but I will now. Show all substitutions, and I will ask you to do that on the test as well. So show all substitutions. And so here, and I clearly didn't give you enough space, my apologies. I didn't realize that until I had really put the document together and it was too late to change. But here, if we're looking at a function, and in this case it's 2/3 times x squared plus 5, whatever is the input inside the parentheses of what I ask you to evaluate for will replace the x when you're computing what the function is. So for example, here in this first question, I ask you to find the function value at -12, or x equals -12. So I'm going to take that -12 and I'm going to substitute it right there for the x. So I keep the 2/3, I substitute the -12 with parentheses because it's a negative number with an exponent, so that's going to be squared, and then bring down the plus 5. And you can type this into Desmos. You would literally type it exactly as it is, but you have to include the parentheses. It won't compute the right answer if you don't include the parentheses. You can try it with and without the parentheses and see if you can prove me wrong. There's the clock. Playing Scott Joplin. I don't know if you can hear it in the background. I'm just going to talk through it. You guys know that clock makes me so mad when I forget when I'm doing a video. And my stove clock says it's 12:57, not 1 o'clock. So I was going to turn it off. Anyway, so type this all into your Desmos or do it by hand. -12 squared is positive 144. Divide by 3, multiply by 2, and then add 5. Excuse me, and you should get 101 for the first one. Now, for -x, I'm still going to substitute negative x for the x, and then put parentheses around it, squared plus 5. And remember that anytime you square a negative, it becomes positive. So this negative x squared is going to become positive x squared. And so that brings us literally right back to where we started, 2/3 x squared plus 5. And in this next one, 2/3 times x plus h, parentheses squared plus 5. And what you're going to need to do for this one is use FOIL with this binomial. So you're basically thinking to yourself, x plus h times x plus h. So take a minute, real quick, pause the video, make sure that you can FOIL x plus h times x plus h, and then what you should get is 2/3 times x squared plus 2xh plus h squared, close the parentheses, plus 5. And when you compute that, you have to distribute the 2/3 across each of those three terms that you got when you FOILed it, and your answer will be ugly, but an answer nonetheless should be 2/3 x squared. And then careful with the 2/3 times the 2 here. 2/3 times 2/1 is going to be 4/3. So that'll be then plus 4/3 xh plus 2/3 h squared. And then just bring down the 5. That can't combine with anything. And so that big ugly thing is going to be your answer to the third part. So there's letter A. Letter B, again, I'm going to substitute the 12 where the x is, so I end up with 4 minus 3 radical 12. And radical 12 is going to be 2 times radical 3. So I am not going to talk through how to simplify a radical, but I'm going to literally replace this with 2 radical 3. And if you're not sure where I got 2 radical 3 from, just shoot me a text or an email and say, hey, where'd you get 2 radical 3 from? Because you're going to need a little bit of work with your simplifying radicals. But then the next thing that I want to do is multiply the 3 times 2, so that my answer here is going to be 4 minus 6 radical 3. In this next one, I'm going to be substituting negative x, and yes, it's a negative x that's going into a radical, and so that's going to come out as an I, so 4 minus 3i radical x. And here for this last one, 4 minus 3 radical x plus h. The x plus h cannot be simplified inside of a radical. It just stays x plus h. So there are your 3 answers for part B. And now in part C, I'm going to substitute that negative 10. So it's negative 10 plus 1 over 3 times, I'm going to put it in parentheses, you don't have to, just make sure that you're multiplying positive 3 times negative 10, excuse me, and then that should give you negative 9 over negative 30. And you can reduce that fraction by dividing on the top and the bottom by 3, or simplify. You all are taught to simplify fractions. And negative divided by negative is positive, and so this whole thing is going to be equal to positive 3 over 10. No decimal answers. Next, I'm going to substitute the negative x. So I've got negative x plus 1 over 3 times negative x. And in the top, you can either write negative x plus 1 over negative 3x, or that might bother your eyes, and so you could rearrange the top if you wanted to that. I would happily accept either of those answers. And then in this bottom one, you're going to substitute in the numerator just x plus h plus 1. In the denominator, you're going to need to use parentheses there, and then you're going to need to distribute the 3 so that your final answer here is x plus h plus 1 all over 3x plus 3h. So for number 3, you're asked to give the domain of each of the following, and there's 6 problems here. What I'm going to do, I am pretty sure, because I already made the Desmos video clips. I made 6 little video clips of me entering these equations into Desmos. So, and what my intention is, hopefully when you watch this video, you'll be like, why is she explaining this? Because I haven't done it yet, but my intention is to work on part A and then insert the video for part A, and then come back to this screen and work on part B, and then switch over to the video for part B, graph in Desmos, and then come back to the screen and work on part C, and then switch over to the Desmos video for part C. So anyway, here if I had a different kind of computer, I could probably do all of that without switching videos. But you're basically looking to find the domain of each. I've asked you not to use any fractions, any decimals in your answers. And some of these are a little bit tricky, and to know the direction of where the graph is going, or where an endpoint is, or where an asymptote might be, a combination of using the equation and the Desmos graph should help you to determine what the domain is. And the first thing that I want to remind you of is that, in fact, let me write this over here, that you only have a restricted domain when you have an x in a denominator if you have an x in a radical, or if you have an x in a logarithm. Remember that I'm not going to test you on anything with logarithms, but then make a note to yourself. All else has a domain of all real numbers. And so I want to compare what I just wrote to letter A here for number 3. And this equation does not have an x in a denominator. It does not have an x in a radical, and it does not have an x in a logarithm. And therefore, the domain is automatically going to be all real numbers. And you're welcome to go ahead and graph it. And in a minute, I'm going to show you the graph of this in Desmos and talk a little bit about how to type it in. But at the end of the day, because this function doesn't meet any of those 3 criteria, then the domain of this function here is going to automatically be all real numbers. And that's my infinity. It was a pretty sorry infinity, and I'm going to make it worse. Probably. Anyway, all real numbers, negative infinity to positive infinity. Number 3a, as in all the problems in number 3, you are asked to find the domain of the function, and I would recommend using Desmos just to get a feel for how the function looks, and then use the equation to actually come up with the exact numbers. Remember that you can't use decimals in your answers. The other thing I want to say about 3a that I probably already said in the other part of the video is that because there's not an x in a denominator, nor is there an x inside of a square root or in a logarithm, the answer to the domain of this function should automatically be all real numbers. You shouldn't really need to look at the graph of this. But real quick, let me just type it in so that you can see 3 minus 5 to the x plus 1 power. Just a note about how I'm typing it. In order to get the exponent, I use Shift 6, which gives you the caret, or that upside down little V shape that we usually associate with exponents on the calculator. We also use that key for exponents in Desmos. I haven't been able to find a way to put an exponent that has multiple terms, meaning a plus or minus, that stays as an exponent. If I didn't type the parentheses, I have found that it'll just revert the plus 1 back down to a full-size number and not part of the exponent. If you have a different way of doing it and can type this in without the parentheses, let me know. But otherwise, I haven't found a way to do it. Neither here nor there. It's quick. There you see that the graph goes forever to the left. And although it's going very slowly to the right, it does go forever to the right, and you could substitute numbers up to, infinity, and all of those numbers are valid exponents to put on the number 5. For letter B, now we have an x in a denominator, and so remember that that's when I'm going to say, okay, my thinking here is that a denominator cannot be equal to 0. So I'm going to take what's in the denominator and say that cannot be equal to 0. And the only way I can make sure the denominator is not equal to 0 is if I say that x does not equal 2. Basically, I'm solving that equation. And if x can't equal 2, but it can equal any other number, 2 is the only number that would make that denominator 0. Therefore, 2 is the only number out of all real numbers. It's the only number that's not in the domain of this function. I'm going to write that as negative infinity to 2. I'm not including 2 because 2 is the number that would make the denominator 0. And then start again at 2, not including 2, to positive infinity. You do see that there's an x in a denominator, and so I will start by typing 5, and then I use the slash that is on the same key as the question mark down in the lower right portion of your keyboard. That automatically switches the 5 to a numerator of a fraction, and then I'll type the 2 minus x in the denominator. And I'll zoom out just a little bit here so that you can see that there is a number missing from the domain here where you can see a vertical asymptote. And I'm assuming that the value of this x is 2, because I see that 2 is 2 minus x in the denominator, and 2 minus 2 would give me 0, which is the thing that you can't have in a denominator, which I have written out for you already. And if I'm really not sure about the value that I have assumed for the vertical asymptote, you don't have to, but you can type x equals, and then I think the asymptote is 2. And I like to make asymptotes red and dashed. And so you can kind of see here that line, that vertical line really does equal 2, and that it's the asymptote for this equation. You don't have to do all of that. You can just visually check the equation of the original function. An x inside of a radical will also trigger a domain restriction. And so again, remember that the inside of a radical, or the expression inside of a radical, cannot be negative. Instead of saying this cannot be negative, though, let's say that inside part has to be greater than or equal to 0. Numbers greater than 0 are not negative, and 0 is not negative. And if the inside of that radical is equal to 0, the square root of 0 is just 0. And so all I'm going to do here is say that the inside of the radical, which here happens to be 2x minus 1, has to be greater than or equal to 0. And now I'm just going to solve this equation. So I'm going to add 1 to both sides. And then I'm going to divide both sides by 2. That x has to be greater than or equal to 1/2. And in a minute, you'll see in the graph, first of all, that the 3 doesn't impact the domain at all, because it just shifts the graph up. So a shift strictly up or down isn't going to affect a graph's domain, because you're only messing with the y values. And so in this case, our domain is going to be from 1/2, including 1/2, going all the way up to positive infinity. And you'll see that in the graph in a minute. For number 3C, I'm going to start typing the radical by typing the letters S, Q, R, T, and that automatically changes it to a square root. And then the 2x minus 1. Remember that because the plus 3 in the equation is outside of the square root, and right now my cursor is flashing inside the square root symbol, I need to press the right arrow key in the bottom right corner of my keyboard to move the cursor outside of the radical, and then I can type plus 3. And that just moves the graph, or transforms the graph up. And if you look here, this point has an x value of 0.5, or 1/2, 3. And so that's going to be the farthest left x value in my domain. And because there's a solid point there is an x value there. That's going to be square brackets around the 1/2, and then to the right it goes to infinity. Please don't skip this problem. I know that I said that I'm not going to test you on logarithms this time, but it's in an upcoming unit, and so we will get to logarithms soon. And so remember that technically, mathematically, it's called the argument. What we're putting into the logarithm, and it's not the input, because x is the input, but what is being entered into the logarithm has to be greater than 0, has to be positive. It cannot equal 0. It cannot be negative. And so what we're going to say here is that our thinking is that 3x plus 2 has to be greater than 0. So 3x has to be greater than negative 2, and x has to be greater than negative 2/3. And in a minute, we'll switch over to the graph. But for now, if x is greater than negative 2/3, not equal. Notice that, sorry about the bouncing video, but there's no or equal to sign here. Okay, it does not include negative 2/3. And you'll see that in the graph, that's where there's an asymptote. And so here, I'm going to say that the graph starts at negative 2/3, not including 2/3, round parentheses, and going to positive infinity because x is greater than negative 2/3. So x is all numbers bigger than 2/3. D. This is the one with the logarithm. I still want you to do the problem. Some of you hear me say, I'm not going to test on this, and you skip those problems. I still want you to do the problem because you need to be practicing stuff with logarithms because we will get to logarithms eventually. So let's take a look at this. If you type the letters log into Desmos, it will automatically change it from those italics to the word log. And then you want to type your parentheses and 3x plus 2 and close your parentheses, and you'll see here that the numbers to the right end of the graph over here go to positive infinity. On the left, though, they don't move infinitely left. Ooh, and I did find where Desmos has a weakness. Almost any graphing software is going to have an issue with a logarithmic function because the logarithmic function has a vertical asymptote, and this part of the graph gets infinitely closer and closer to the asymptote. What you'll find is that around here, Desmos or your graphing calculator or any other technology that does graphing will probably kind of freak out a little bit and say, ooh, this isn't a function because it got vertical. And so this does actually keep going down and gets closer and closer to your asymptote. And what we should have computed in the other portion of the video is that the asymptote here is at negative 2/3. And again, if I want to double check, I don't know why my computer froze. If I wanted to double check to see that that's really where the asymptote is, I can again graph that line x equals negative 2/3, and that should give me an idea that asymptote is approximately the same place. And you would really have to zoom in here to a great magnification to really see that it doesn't actually ever touch the asymptote. And at some point, the lines are just too thick to tell that. So anyway, here's your graph for number 3D. So in this problem, this is a lot like letter C that we just did a couple minutes ago, where you take the inside of the radical, whatever is the inside of the square root. That thing that I just highlighted yellow cannot be negative. It can be 0 and it can be positive. So our thinking is going to be here, think 7 minus x squared has to be greater than or equal to 0. So I'll add x squared to both sides. So 7 is greater than or equal to x squared. And then I'm going to take the square root of both sides. But remember here that when you take a square root of x squared and of a number on the other side of an equation to solve an equation, you have to consider both the positive and the negative square roots. So I'm looking at plus or minus square root of 7 is greater than or equal to just x. And in a minute, when you look at the graph of that function, which you can type into Desmos now, and I'll talk about that in a minute, you'll see that that's one of those graphs that looks like a semicircle or a half of a circle where both end points of that semicircle are right on the x-axis. And those endpoints are your plus and minus radical 7. So it goes from negative radical 7 to positive radical 7, but because those endpoints are still points on the graph, radical 7 and negative radical 7 would make the function equal to 0, or what's inside the square root equal to 0, and the square root of 0 is 0. You're going to include both positive and negative radical 7. So your domain is going to have square brackets on both ends, and from negative radical 7 to positive radical 7. In number 3E, it's a different version of a graph that has a square root. So let's type in the SQRT, and then you have 7 minus x squared. And in this case, with your x squared, that x squared inside of the radical in this equation tends to give you this semicircle situation here. And so I can see that the graph goes from some x value over here to some x value over here, and there are actual points there. They seem to have the same numerical value. One is positive and one is negative. And then in the other part of the video, we computed those to be radical 7, so it's negative radical 7 to positive negative radical 7 here to positive radical 7 here. And we used square brackets on both ends, both the negative radical 7 and the positive radical 7, to show that those 2 points are included in your set of all x values. Now for letter F, there are 2 things to consider. There's the numerator, which has a radical, and the denominator, which can't be equal to 0. So what I'll start with is the numerator, and I'll say, okay, you need to think to yourself that 8 minus x, the inside of the radical, has to be greater than or equal to 0. 8 has to be greater than or equal to x. And for the denominator, you're thinking to yourself that x plus 3 cannot equal 0. So x cannot equal negative 3. What's going to happen, in a minute you'll look at the graph, is that you're going to find that you have an asymptote at x equals negative 3. So this is going to be an asymptote. And you're going to have an endpoint at positive 8. And all x values are going to be to the left of or less than positive 8. 8 is bigger than all x values. And of all those x values, you are not going to have a value at x equals negative 3. And so when I write my domain, I'm going to go from negative infinity to negative 3, not including negative 3 because that's an asymptote. And then from negative 3 to positive 8, including 8 because there will be an endpoint at 8. So stay tuned for that video. Last but not least, number 3F has a twist because it's got both a radical in the numerator and an x in the denominator. And so we have to take both of those things into consideration, which we should have worked out algebraically in the first part of this video. And so I want to start by, oh, and also I said something in my lesson 7 video that I didn't know how to start a fraction that had multiple terms in the numerator without actually typing parentheses there. And thank you to those of you who are quicker with Desmos than I am. I had a couple of students say to me, hey, if you start by typing the slash, so the divide sign that you use to create a fraction, if you start typing that at the beginning, then you will see that it automatically gives you a fraction and invites you to type something in the numerator, and then you can use down arrow or your cursor, your mouse pad to click on the denominator and type in the denominator. So anyway, I'm going to start my fraction by clicking on the divide sign, and then my SQRT to get the square root, 8 minus x in the numerator. And then I'm going to down arrow to the denominator and type x plus 3 there. Let me see if I can get more of this in the picture. So it looks to me like I have an asymptote right about here, and that the graph ends entirely there at x equals 8. So this part of the graph, the fact that it ends at x equals 8, is reflected in the numerator of the fraction. And the asymptote that we have here at x equals -3 is reflected in the denominator of the fraction. And again, if you wanted to check your asymptote, you would just type x equals -3. And again, you're not required to type the asymptotes. I just like to look at it to make sure that I've got the right idea about what the number is. In number 4, I'm going to give you graphs, and I want you to come up with the domain and range of each graph. And so in this case, and folks, for the graphs that I give you, I want you to assume that if the graph goes to the end of the graph space, see how you can kind of tell here that I cut and pasted it? You can tell right here that I cut and pasted it. Just assume that no, I have to get rid of it. Not as easy as the app I use in class. Just assume that goes then to infinity. So assume arrows here and here. And so your domain is going to go infinitely left and infinitely right. And so your domain will be all real numbers. There's no other breaks in the graph. But your range starts at the bottom at -infinity, but it tops off here, right there, at y equals 5. And it touches. So this point, if I were to ask you what's the vertex, what is the vertex of this function, it would be like 1.8 or something, -1.8 comma y equals 5. And so your y value is 5. And so we'll include 5. So I'm going to put a square bracket around the 5. The only time really that you're going to use round parentheses is if it's an asymptote, if it's an open circle, or if it's infinity. In interval notation, those are the 3 times that you'll use round parentheses. Now, again, in letter B, assume these graphs keep going beyond the edge of the graph space. Also, ignore that it doesn't quite touch the x-axis. Assume there that it touches the x-axis at 1 and negative 1. So my domain is missing x values between negative 1 and positive 1, where I just shaded pink. That is really a pale pink. You might not be able to see that. And so the domain is going to be in two parts here. And this part here goes from negative infinity to positive, or negative infinity to negative 1. And this part here goes from 1 to positive infinity. And so we'll write that parentheses, round parentheses, negative infinity to negative 1 with a square bracket, and then positive 1 to positive infinity, round parentheses around the positive infinity. Then the range is a little bit different, so I'm going to erase all the scribblies that I put all over the, well, some of the scribblies that I put on the graph. I'm going to get rid of the red and maybe the pink. But the range is only going to be written as one segment. So remember that your range, well, domain and range is looking at all, the range is looking at all y values. The domain looks at all x values. And so when I'm looking at the range, because I have, for example, a y value here and here, I'm only going to list y equals negative 2 in the range once. And because it goes to negative infinity here and negative infinity here, the bottom of the graph is negative infinity. The top of the graph is 0. And so this whole graph happens between negative infinity and 0. And so my range is going to be negative infinity to 0, and it includes 0. Now, what I want you to notice in letter C, I'm going to go back to the pink, sorry. What I want you to notice in letter C is that there's no x values between x equals negative 2 and x equals negative 1. And so my domain is going to be in two pieces. And I'm going to start with this piece over here, excuse me, and it starts at negative 5, but it is an open circle at negative 5, and so it starts at negative 5 with round parentheses, and it goes to a closed circle at negative 2, so it's going to be negative 5 to negative 2, not including negative 5 and including negative 2. And then union, and then I'm going to have, again, I start now with this second piece of the graph, a closed circle at negative 1, so it'll be including negative 1, and then at the other end it goes to infinity, and so it'll be negative 1 including negative 1 to positive infinity, round parentheses around infinity every time. Now, to talk about the range, I'm going to erase all the pink here, all my scribbling. And remember, again, that domain is about, range and domain are about all the x values or all the y values. So the range is what's the very bottomest part of the graph. It's right here. We're not missing y values here because they happen over here. And at the top, it goes to positive infinity. So your range starts here at negative 5 and goes up forever. And there's no y values missing because of this portion of the graph that's right over here where I'm drawing the dots. And so the way I'm going to write my range is to start at -5, including -5, and go to positive infinity like that. Now in letter D, the important thing that you have to keep in mind is that this open circle or hole in the graph affects both your domain and range. And so the point that's missing has an x value of 6 and a y value of -5. Is a hole in the graph, or is missing from both the domain and the range. And so the other thing that you want to know here is that this point is -3, 1. And so your domain goes from here to missing this point and then to infinity. So we go from -3 to the whole, and then from the whole to positive infinity. So -3, and it's a point there where it's -3, 1. So there is a point, so there is an x value, so we're going to use square brackets, -3 to x equals 6, but at 6 there's a hole, and so I'm going to do not including 6, and then go to positive infinity. And that 6 looks an awful lot like a B, so I'm going to change that. Hopefully that looks more like a 6. And then my range, now careful, remember that this graph goes down forever, and so the range starts at the bottom, that's -infinity. It comes up to the hole, and then past the hole it continues up only as far as where that endpoint is. So my range is going to start at -infinity. It's going to come up to the hole at -5. It doesn't include -5, so you put round parentheses because it does not include -5. And then it goes up to that endpoint at +1. In problem number 5, you will need to be able to look at the graph of a piecewise function and determine the value of the function for given inputs. So meaning you're going to need to find a y value to match the given x values. So for example, in letter A, you're asked to find f of -6. -6 is an x value, and so you're going to look at -6 on the x-axis, and you're going to follow it up to where the function is on the y-axis, and there's a point right here at -6, +5. Right, that's the y value at where x is -6, and so your answer there is going to be 5. And then where x is -2, I'll go and I lettered these wrong. I'll catch the other column in a minute. Where x is -2, remember that you're looking at two possibilities, but because this one is an open circle, it's not the -5, it's the one that's the closed circle at +4. And so f of -2 is going to equal 4. F of +2, there's +2, and the only possibility for that one is also +4. And f of 4, well here's 4, and the function is right there at -2, so f of 4 is -2. Now skipping over here, when f is -4, I'm just going to kind of zoom in here. The graph crosses the x-axis here, and so that's y equals 0. So f of negative 4 is 0. F of 0 in the next problem, that's actually just asking for your y-intercept. Where x is 0, you have a y-intercept. Where x is 0, you have a y-intercept, and so that's going to be positive 4. And where x is 3, 1, 2, 3 here, be careful because you've got two choices. It's not the open circle, it's the closed circle. And so that's going to also be 4. And then f of positive 5. I would say, this is kind of hard to read, but I would say that that's positive 1. And so f of 5 is going to be 1. Now in number 6, I'm essentially doing the same thing, but this time with equations. And so I need to kind of keep track, and I'm gonna color code these. So this top equation is for everywhere, or for all x values less than but not equal to 4, negative 4. The middle equation is for x values from negative 4 to positive 2, including negative 4, not including positive 2. And then this bottom equation is for all x values from positive 2, including positive 2, and on up to positive infinity. And so what I'm going to do is look at the different x values and say, okay, negative 7 is less than negative 4. And so when I compute that, and I do want you to show your substitutions. I didn't say that. Why didn't I say that? Wait a second. It'll be in the directions soon. Show substitutions. Oh, and your answers should be simplified with no decimals or parentheses. No parentheses either. These may be in your directions by the time you get this packet. Anyway, negative 7 is less than negative 4, and so I'm going to substitute that into negative 4 times negative 7 plus 3, and so your answer for this number, Roman numeral little 1, is going to be positive 31. I'll go this way, f of negative 4. You know that I'm going to ask you the values at the transitions. So we're negative 4 and positive 2. I have asked you about negative 4 and positive 2 because that's where the transitions are, and you need to make a decision about whether to use the first equation or the second equation. So here you're looking at the less than or equal to sign, and so you're going to use the second equation for f of negative 4, and so I'm going to substitute negative 4 to the third power, negative because of this, and then negative 4 into the x, so you have that negative sign twice. But negative 4 is negative 64. Negative 4 cubed, is negative. So when you cube a negative number, you get a negative answer. But I still have that negative that I started with, and so your answer to that whole problem is just going to be positive 64. Make sure you track with where all those negatives went. For f of negative 2, negative 2 is in the green shaded section or equation. It's between negative 4 and positive 2. And so I'm going to substitute negative 2 into the x cubed, and that'll give me minus negative 8, which is just positive 8. I'll do a lot with zeros as well. Don't be surprised to see zeros just about anywhere, because 0 is a common input that you need to analyze. And so 0, again, is in the green section because it's between negative 4 and positive 2. And so negative 0 cubed. Well, 0 can't be negated, so the whole thing is just equal to 0. 0 times 0 times 0 is 0. And the negatives aren't going to affect 0 one way or another. I missed it again. Not paying attention. At least it plays different songs so you can be entertained differently each time. Oh boy. So the positive 2 then, because in this equation there's no equal sign there, the positive 2 then is going to go into the pink equation. And so f of positive 2 gets substituted into the 3x squared. So 3 times 2 squared plus 1. 2 squared is 4 times 3 is 12, plus 1 is 13. And last but not least, 5 is bigger than everything else, and so 5 is going to be substituted into the last equation there. And so that's going to be 3 times 5 squared plus 1. And when you compute that, you'll get 76. Please don't take my word for it. Don't just copy what I wrote, but please write, or please take the time to pause the video and compute the problems for yourself. Now I'm going to do the same process here in letter B. I am going to now this top equation basically says that if I have an input that's less than negative 5, my answer is 15. It's not going to be any computation at all. It's going to be negative 15 for every possible number that's less than negative 5. And that's what would graph a horizontal line. I know I'm not asking you to make a graph here, but it would graph a horizontal line. In the middle, then this is for all x values between negative 5 and positive 10. And then in the bottom row, for all x values greater than 10. And again, before you even start to look at the inputs, you know I'm going to ask questions about negative 5 and 10, just because those are where the transitions are, and they're the hardest to decide which equation to use. So in number 1, negative 19 is most definitely less than negative 5, and so negative 19 is going to get plugged into the first equation, but wait, there's no plugging in that needs to happen. Your answer is just negative 15. But when it's exactly negative 5, remember that we're looking for the little equal sign. It's not here, so it's got to be here where you've got less than or equal to. So we're going to use the green equation for exactly negative 5. And so now I'm going to do the radical negative 5 plus 6, which equals the square root of 1, and radical 1 is just 1. Zero is also between negative 5 and positive 10, so that's going to use the middle equation as well. And so that's going to be radical 0 plus 6. 0 plus 6 is just 6, and so my answer here is just radical 6. And 4 is also between negative 5 and 10, so that's also going to be the green equation. And so that's going to be radical 4 plus 6, and that is radical 10. And radical 10 cannot be simplified at all, so that's just your answer there. Now again, 10 itself is included here and not here, and so the 10 is going to be the green equation in the middle, and so that's going to be radical 10 plus 6, which is radical 16. Wow, Apple Walker gave you an even perfect square to put into a radical, and so your answer is straight up 4. Crazy that I did that. I should change it. And then last but not least, 12 is greater than, so I'm going to go back up and erase my scribbling there, but 12 is greater than 10, and so the last one, the 12, is going to be substituted into the last equation, or the pink, and so that's going to be 2 over 12 plus 8. Well, 2 over 12 is equal to 1/6 plus 8, and so that whole thing just equals 8 and 1/6. And you can leave that as a mixed number. I'm fine with that. You don't need to change that to an improper fraction. If you were going to then go and take that answer and multiply or divide it by something, or add or subtract it, you might want to change it to an improper fraction. But in this case, please just use 8 and 1/6 as your answer. Now, for number 7, hopefully you'll see me walk through these graphs on Desmos first, and then I will draw them by hand. And what I would do if I were you is do it in that order. You will be asked to draw one piecewise graph on your test, and I'm going to say that if I were you, I would draw the graph on Desmos first. Make sure you understand the different pieces of the graph and where the different points are on the graph, and just remember that Desmos won't show you the open and closed circles, and so you'll just need to remember how to do open and closed circles without the help of the. This is the video for number 7A, and what I'm hoping to be able to do later is to superimpose the equation here in the video of the graph. So hopefully right now as I'm talking you're wondering what I'm talking about, because it's already there. Hopefully it's already there. And so you're looking at a piecewise function equation that has 3 pieces to it. And I will start with the top piece. So remember that when you're entering piecewise equations into Desmos, you want to enter each piece into a different line of Desmos. So I'm going to start up here, and I'm going to start with the absolute value portion of the graph, and I'm going to type the ABS for the absolute value, x plus 4 parentheses, and then minus 1. Now, the problem to start with is that your Desmos just starts by graphing the whole function, and then you need to tell it, no, I want a piecewise function. So you're going to look for the curly brackets. Ignore my notifications, please. Thank you. You're going to look for the curly brackets. Soon it's going to tell me that my hard drive is full, so keep watching for that one too. So I'm going to find the curly brackets are next to the P button, and you have to press shift, and they share the same key with the square brackets. So I'm going to type open curly bracket, and then it says x is less than -2. So I'm going to type x, lowercase x, less than -2, and then I'm going to close my brackets. Remember that Desmos is not going to show you a closed or an open circle on the endpoint unless you actually click on the endpoint, and then it can show undefined. But the minute that you let go, it lets go of telling you that it's undefined. So just keep in mind that you are responsible for knowing where to put closed and open circles when you draw the graph, but using Desmos to help you decide where to put the lines and the curves and the different points. The second part of this graph is just the horizontal line y equals 1, which isn't going to graph anything when you first type the 1, but then you're going to do your curly brackets, and then -2 is less than or equal to, you type the less than, then you type the equal sign, and it gives you less than or equal to x is less than 3, close the curly brackets. And now I have this part of the function. So the blue is the absolute value, the red is the constant part, or the constant piece. And then the third part of the equation is negative parentheses x minus 5 squared plus 3. And again, I need to give the curly brackets to tell Desmos to just give me a portion of this piece of the function. So it's x is greater than or equal to, type greater than, and then the equal sign, 3, and close the brackets. Oh, and let me change the color so I have 3 different colors. And so that is what your graph should look like. And then what I would do to help me draw this is I would just say, okay, well, it looks like I have a point at -7, -2, and or +2, -7, +2, and then -6, +1, and there's a point at -5, 0, -4, -1, -3, 0. The constant here is at y equals 1. Remember that if you're going to draw a straight line, I would like for you to use a straight edge. Grab a piece of scratch paper and fold it, or ask me during the test for a piece of paper, and I can give that to you, and you can fold it up and use that as a ruler. And then over here, I would look for the points that are graphed in Desmos as important points, although maybe not those decimals. So you've got the vertex of your graph here. You know that you have a point at 3, -1, and you should also have a point here at 7, -1. And just graph as many whole number points as you can to give you an idea of where the graph is. Maybe put an arrow down here, and then in the other part of the video I'll show you where the closed and open circles go with the different other points of the graph, as well as the domain and range. Software. So anyway, here we saw that the absolute value portion of the graph, let's see here, what color am I using? So the absolute value portion of the graph has a vertex at -4, -1, and it has a slope of 1. Remember, you're going to use a straight edge to draw this, and the first equation is where x is less than -2, and so it's going to go to here with an open circle and be like this. And let me just make that open circle better. And so that, just to kind of show where I am, that's the first piece of the equation. Then the second piece of the equation is at +1 from -2 to 3. So those two equations are going to overlap just in that one point. So let me do this maybe in purple. So the second equation is going to be a horizontal line because it's a constant. Anytime you have just a number like this with no x value to compute with, you're just going to draw a horizontal line. So y equals 1 from -2 to +3. So from -2 to +3, and then at +3, let me just cut that back a little bit. At +3, we want an open circle here. I'm going to make that just a little bit heavier. I'm making it worse. And so there's an open circle there. And then my last equation, what color? I'm so bad. How about green? So this last equation I'm going to do in green. and it's a parabola that opens down, or quadratic that opens down, and it has a vertex up here at positive 5 comma 3. So I'm going to put a point up at 3, and we found in the Desmos graph that it has points at 4, 2, and 6, 2, and then 3, negative 1. So this is going to be a closed circle because of the equal sign here. And this graph is going to kind of go like this, and then like this. And I will basically check to make sure that your graphs are fairly accurate as far as where do the points go, and also make sure that you have the open and closed circles in the right places. So the only place on this graph that you have an open circle is at negative 3, positive 1. That's this spot right here is the only place you have an open circle. But also make sure that I can see that you've got a closed circle down at positive 3, negative 1. Now, I was not successful at writing equations for anything on this test that really had tricky piecewise domain and range. But if you look closely at this, there's no x values missing, not even in the section where there's the gap between the two functions. There's still no x values missing, so your domain is negative infinity to positive infinity, all real numbers. Your range also, because it goes here to negative infinity and here to positive infinity, and there's no breaks in the range either. All the y values are covered, so we're going to say that the range is also all real numbers, negative infinity to positive infinity. So this is the video for 7b, and again I'm going to type each piece of the function into different lines of Desmos. And so the first piece is just x minus 1, curly bracket, x is less than negative 2, close my curly brackets. There's the first piece of my function. Now remember that if x, and I'm going to type this in the way it's not going to work. I'll show you that if you just type negative 1 for x equals negative 2, it's not going to give you a point, because here your x value is just one number and your y value is just one number. Desmos isn't going to show you that point. But you can trick Desmos into showing you the point if you type it as an ordered pair. So the x value is negative 2, the y value is negative 1, and so you type with parentheses negative 2 comma negative 1, and it gives you a point there. So we already know that this function, the blue part, is not defined for x equals negative 2, that the function, the whole function is defined at x equals negative 2. And the point, I'm not redoing this video. You're just gonna have to look at my phone call. That was a spam call anyway. So negative 2, negative 1 is where so the function is defined at x equals negative 2 as being negative 1, and that's the only place where it's defined at negative 2. So it's not part of a piece of another piece. And then the third piece of the function is 1 over x plus 2, and that is where x is greater than negative 2. And in this piece of the function, this is, oh, look at that. Sorry, I missed that and started talking. And it looked like it did what I wanted it to do anyway, which is kind of crazy. Okay, better. So what I see here is a piece of a rational function And you've got a point here at 0.5 and -1, 1. That should be enough to give you the shape of the function. There's an asymptote at -2 that would be here. And we'll talk more about horizontal asymptotes with rational functions in the next unit, but there would be a horizontal asymptote at y=0. So when you draw this on your paper, the vertical asymptote at -2 and the horizontal asymptote at y=0 should give you a feel for what the shape of this third part of the graph would look like. And this point in the middle, I'm not checking what you're putting into Desmos. And so you really don't need to worry about graphing that. If you know where to graph that point, you probably didn't need to type it into Desmos in the first place. And so really, if graphing this much of it helps you place the rest of the graph where it needs to be, then you're all set. So hopefully you just watched a video of me graphing this one in Desmos, so you have a feel for the one in the middle that's a dot, or just a dot, a point, a finite point on the graph, and the bottom equation that creates part of a rational function with asymptotes. And so here, let me do the top equation I'll do in blue, and the middle equation again I'll do in purple, and the bottom one in green. And so the blue one, remember that the idea is that you're thinking about graphing. If it was just x minus 1, you would start at -1 and you would have a slope of 1. But you're not going to graph that whole line. You're not going to graph all of that, because you have to stop at -2. So you're literally just going to graph that much of it, but you need an open circle at -2 because it doesn't include -2. So there's no equal sign there. So let me fix this up just a little bit. I'm going to have, in fact, I'm just going to erase all of that. I'm going to have an open circle here, and the open circle, the point where the open circle is -2, -3. And if you look at what you have in Desmos, you should have that as well. And then my slope goes down one, or yeah, you're going backwards, but it's a positive slope, but up 1 over 1, up 1 over 1, slope of 1. Then that middle thing, the purple, is the point -2, -1. It's where x is -2, and that's the -1 is your y value. So x is -2, y is -1, and that's a finite point right there. And that should look a lot like a closed circle. Now, this last portion, when I talked it through on Desmos, I talked about there being asymptotes. The horizontal asymptote would be at y=0, and you don't have to draw the asymptotes, and I'm not going to put a rational section on the piecewise function on your test for this unit because we're going to be graphing rational functions in the next unit, but just imagine that there was an asymptote here as well. And so your rational function there goes through, using green, goes in this upper right portion of the graph, and it goes through points like 0, 1/2, and 1, -1, 1, and so on. And from those places, it's going to get closer to the asymptotes. And this is kind of tricky for me to draw on the iPad and have it be accurate, but this is kind of what we're looking at for this graph. I'm going to make it worse. I hope not. So there's that point in the middle. I can't live with it. I'm sorry. There. Hopefully that's a little bit better. Now, again, like I said, I failed at trying to come up with graphs that were not all real numbers for both the domain and range. So, oh, the range isn't all real numbers. What am I thinking? The domain is all real numbers. And here's why. If you were going to give the domain of each piece, the blue section goes up to but doesn't include x equals -2. But x equals -2 is included here. So -2 is not missing from the graph. Nothing to the left of -2 is missing from the graph. And the minute that we get up into the rational portion of the function, everything to the right of -2 is included. Because remember, by definition, a rational function is from the asymptote and on to infinity. And so it would be round parentheses 2 to infinity. But we've got 2 at a different part of the graph. We've got the 2 here. And so our domain is still going to be all real numbers. But now the range, let's take a look at the range. The range goes from -infinity here up to, but not including, -3. So the range starts at -infinity, goes to -3, does not include -3 because of that open circle. Oh, yeah, and I wouldn't give you anything like this on a test because this is hard to write. Then you would have y equals -1. I couldn't even write this in interval notation because that middle part's not an interval. Union 0 to positive infinity, but then you'd have to have ny equals 1. Let's write this in -1 in set notation. Then x is less than but not equal to -3x y. Dang. Do not worry about this problem. Y equals -1 and y is greater than but not equal to 0. That would be your range, and it's ugly. Bleh. Don't worry about the range here. I'm going to get my black ink, and I'm going to say, don't do this. Don't do the range here. Don't you worry about a thing. Don't worry about the range. Okay. So here for number 8, I gave you the graph of a piecewise function, and I want you to see if you can come up with the equation of it and also give the domain and range. Hint, once again, the domain and range are all real numbers. They won't be on the test. I will actually give you some variety on the test. So I just had already done this when I realized that they were all real numbers. So remember that you're going to have 3 pieces to this function, and I'm going to kind of color code them so that you can see what I'm doing as I go. I'll make this one green, and I'll make this last one pink. And so for the yellow one, when you're working with a linear segment, you kind of want to just keep going. So this slope is down 2 over 3, and so you kind of want to keep going down 2 over 3 just to find the y-intercept. So your y-intercept is -2, and we said that the slope is -2 over 3. And so the equation of this line is y equals -2/3 x minus 2. Y equals mx plus b. I know that's hard to see sideways. Y equals mx plus b. So the equation of that line is y equals negative 2/3 x minus 2. So that's going to be the first part of the equation is f of x equals, and then it's negative 2/3 x minus 2. And we'll come in and fill in the restrictions in a minute. The middle one, the one that I have in green, is just y equals 3. And so that's going to be a 3 right here, and we can fill in the restrictions in a minute. And this last one is an absolute value function, and the vertex of the absolute value shifted to the right 3 and up 3, and there's a flip. So this would be the absolute value of x minus 3, that's to the right, and then up 3, that's plus 3, and a flip is the minus at the beginning. And so that equation is going to be negative absolute value of x minus 3 plus 3, and we'll fill in the restrictions next. If you guys had any idea how many mistakes I have in the draft copy of this that I did, it would be a wonder that you ever get correct answers to these. My apologies if I'm hesitating here and there, because that's when I'm seeing my mistakes. I had some crazy stuff for this absolute value equation. Anyway, so the yellow portion of the graph, the linear equation that I have in the top, is from negative infinity to negative 3, and it includes negative 3. So we don't deal with the infinity, we just say if x is less than or equal to negative 3, and that shows that we include the negative 3. The green section in the middle, this y equals 3 part, doesn't include the endpoints, but we have here negative 3 and here positive 1. And so this is going to be from negative 3 less than x, to positive 1, not including either negative 3 or negative or positive 1. And then the last part of the graph starts here at positive 1, including the positive 1 because of the closed circle, and goes to infinity. And so we're going to say if x is greater than or equal to positive 1. And if you look closely at this graph, like I told you earlier, there are no missing x or y values. The range, to be sure, goes from negative infinity to positive infinity, and there's nothing missing in between. And same with the domain, every x value is covered. And so here, domain negative infinity to positive infinity, range negative infinity to positive infinity. Number 9 and 10 get into the floor and ceiling functions. Remember that the notation for the floor has the little half bracket at the bottom, and that just means round down. And the one that has the half bracket at the top, that's ceiling, and that has the half bracket at the top, and that's round up. So if you have a floor function and you're asked to round down, floor function of 3.8 is just 3. Floor function of a negative number, remember that rounding down, then negative numbers go in the opposite direction, and so it'll be negative 10. For your ceiling function, the ceiling for negative 5.7 round up, so that's going to be negative 5. And remember that for any of them, put a little star by this if you need to remember that for any of them, if this is a whole number, or an integer is more specific, if that's an integer, it's just going to be equal to itself. So there's no change, because when you round a number that's already rounded, it just stays the same. So in number 10A, again, I hope that for number 10A and B, I have been able to figure out a way to incorporate the equation at least from the worksheet into the video that you're looking at of the graph. And I think it's especially important for this one because in Desmos, there's not a way to type the notation of the floor and ceiling functions the way that they are given on paper. So you have to be able to recognize the floor function and the ceiling function notation on paper. But then when you come to Desmos, you just type the word floor or the letters CEIL to get the actual function. The other problem is that the Desmos isn't going to give you any hints as to where the open and closed circles go. So you need to remember them on your own. And I think that I will talk through those in the other video. Excuse me. But what I'm going to do here is graph 10A, which says the floor function of x and then -3 outside of the brackets. So I'm going to type floor and then x and then close the parentheses. Now, before I include the -3, notice that I've got the parent graph of the floor function, and unfortunately, Desmos gives you both of those as closed circles, even though the floor function actually would be undefined at this point and defined here at 1, 1. This shows it not a function, and that's not correct. So when you draw that, you can't draw it that way. Anyway, coming back up here, I'm going to shift this function down 3, so -3. And what I would do if I were you is then compare. So we've talked about in the other portion or we will talk about. I think I'm going to put the video of the graph first and then show me graphing it. But the floor function would have, the apparent graph would have the closed circle at 0, 0 and the open circle at 1, 0. And so you're shifting that line segment down 3 to be this line segment. So your closed circle would go here on the left and your open circle would go here on the right. So for all of them, closed circle, open circle, closed circle, open circle, closed circle, open circle, the closed circle on the left and the open circle on the right. So hopefully I have already integrated the video of the Desmos version of this. So we've talked through the fact that Desmos won't give you the closed and open circles, but they can kind of give you an idea of where to put the line segments, where they start and end, and how far away from each other they are. So if the step is 1 unit high or 2 units high or whatever. So in this first example, it's the floor function. So that the parent function of the floor function would be like this. I'm not going to draw all the steps, but the parent graph would be like this and would be up 1 over 1 each time. So this would be the parent floor function. And in Desmos, and because you understand transformations, this whole thing would be shifted down 3. And so then Desmos showed you that these are now going to each be like this, still 1 unit apart. And I like to just graph all of the closed circles first, just easier for me. You can do this however it works best for you. And then just fill in the other parts. And for 10b, it's asking you to graph a ceiling function that has both a flip, that's the negative, and a vertical stretch factor 2, that's the -2 times the ceiling function of x. So I'm going to type -2. I'm going to type a times sign. I think you probably don't have to, but I like to be extremely clear when I'm talking to computers because, you know, they don't always do what I want them to do in my head. So -2 times and then CEIL. Notice that when you type those letters, then it automatically changes to the function ceiling, and then you type parentheses x, close the parentheses. You should see that this is the vertical stretch without the -2. I'm going to do that real fast. This is the ceiling function without the -2, and each step is one step or 1 unit up from the previous step. And if I were to pull in the 2 times, I know I don't need the times sign, but I'm going to type the times sign. That stretched it by 2, and hopefully you can see that now there's 2 units between each step. And then I'm going to put back the flip, and there's the minus, and that flipped everything over the x-axis. Remember that in the ceiling functions, your closed circle is at the left, or the right, I'm sorry, the closed circle is at the right end of the line segment, and the open circle is at the left end of the line segment. And so then you would repeat that pattern all the way up. And again over here, I hope that I have successfully spliced the Desmos video in before you hear me saying these words. So remember that this is both a flip and a stretch of the ceiling function. The ceiling function still has its closed circles. The parent function of the ceiling function has the closed circles at the origin, but this time they go to the left to get to the open circle, and they would also go like this. So this is the parent of the ceiling function that I'm doing in pink here. So this is the parent ceiling function. But we want to flip that. Let me make a little note here that this is a flip and this is a vertical stretch. And so the stretch, excuse me, so the stretch, and I'm running out of colors. I think what I'm going to do here is erase the parent and show you the stretch in pink, and then I will give you the flip in the final color. So back to the pink. So the stretch would start with the original or the middle portion in the same place, but instead of the next portion being here, it would be stretched by 2, and so it would go to here, and then up to, it would go to here, but that's just a stretch. And so then I would take each of those pieces and I would flip them down across the x-axis. And so my final graph would still have this piece here in the very middle. That piece never moves anywhere unless I actually shifted the whole graph. But then the piece that shifted up to now is, or stretched up to, is now going to stretch down to, and then this one here is going to stretch or flip down to here, and again down to like this, and so on. That's too big. Yeah, I'm a little picky. And then I'm gonna, too picky. So these last three questions at the bottom of this page basically ask you, first of all, to talk about symmetry, and secondly, to look at whether it's an even function or an odd function, or neither. And here I didn't give you any that aren't functions, so you don't have to worry about that trick. It has symmetry, but it's not a function, therefore it's not even or odd. And basically, these first two are a good comparison. So the first one is going to end up as an odd function, and the second one's going to end up as an even function, and I'll talk you through how you can tell. For the odd functions, what you want to do is look at the very middle of the graph at the origin. And so if I look at the origin, and I would, even if I were you and not sure about this, I would literally take my pencil and put the tip of the pencil on your piece of paper right there on the origin and spin the paper 180 degrees. And if when you spin the paper 180 degrees, the portion of the graph that was here ends up down there, and the portion of the graph that was down here ends up here, and same with the other pieces of the graph. If this ends up here and that ends up down there, then it has what we call rotational symmetry, which means you can rotate the graph and it is the same, or it appears the same, or it has the same shape in the same place. In this case, in order for it to be odd, it has to have rotational symmetry of 180 degrees around the origin. So the first question says y-axis, origin, or neither. And here it has symmetry about the origin. I guess I didn't even ask about the x-axis. So it has symmetry, rotational symmetry about the origin, and that makes it an odd function. Now this next one I had said is even, and the reason that it's even is because if you look at the y-axis, and if you were to fold your paper, actually fold your paper in half, or mathematically, if you were to reflect this shape across the y-axis, it would appear exactly the same, or it wouldn't change at all. And so this has symmetry across the y-axis, and it is an even function. And in this last example, if you look at the y-axis, it does not have reflection symmetry over the y-axis. If you look at the origin, it clearly does not have rotational symmetry about the origin. Now, it looks like it has rotational symmetry, but it's not about the origin. And if it's not about the origin, then we have to say it's none of the above. And so this has none of the symmetries that we're talking about. Therefore, it's neither even nor odd. So for number 12, and I have mentioned this in class, and I want to stress that if the question says show algebraically, you can still check your answer on the graph. I don't care. You're going to have Desmos for the whole test, and we'll talk in class about what that's going to look like, but you can assume that you have access to Desmos for any question that you want. It's just that when I say that you need to show algebraically, in this case something is even or odd, or in some cases it might be the computing the x-intercepts or the y-intercepts or zeros. You can check all your answers against what you see on the graph. That, in fact, I would if I were you, but I am asking you to show me the algebraic steps on your paper. And so if you would go ahead and take a look at letter A. By the way, I am going to try to include a screenshot of the graph of each of these functions in the video, like kind of overlay picture in picture of the screenshot of the Desmos graph while I'm working on the equation portion of it. So if I am successful, hopefully you're going to see that coming up right now. So anyway, what I would do for each of these is to look at the graph of the function and kind of in my mind think, well, I think this is an even function, or I think this is an odd function, or I think it's neither even nor odd. But then I would come back to the fact that you have to show algebraically and remember that for all three, even functions, odd functions, or neither, you start the same way by substituting negative x for the x values. And so this ends up as negative x in the numerator over negative x squared minus 16 in the denominator. Now, when I looked at the graph of this, I thought it might be odd, and hopefully you're seeing that on the side of your screen here. And so in this case, when I simplify, which is the next step, and you're really only going to have two algebraic steps for any of these functions, but the next step then is to simplify the expression with the negative x's. And so f of negative x. Now that negative x in the numerator stays negative x. The negative x in the denominator becomes positive x squared. And remember that in a fraction, if one or the other, if either the numerator or the denominator changes sign, the value of the entire fraction has changed sign. So that whole fraction now is negative f of x, because that whole fraction has become negated just because the numerator was negated, even though because the bottom stayed the same and the top changed, then the whole fraction is negated. And that is what makes something an odd function. An odd function is when f of negative x becomes negative f of x. That's your odd function. And so here my answer is going to be odd. In letter B, when I look at the graph of that, that's one of those graphs that gives me a little half circle where the two ends of the half circle or the semicircle are on the x-axis, and they're equidistant from the origin. So I would say that that's probably an even function. And so here I am going to substitute negative x. And again, negative x squared is just positive x squared. And so f of negative x is equal to radical 10 minus x squared. And that's really where we started. And remember that an even function, f of negative x, gives me the original function f of x unchanged. And that's what we have here, is an even function. And so letter B is even. Letter C, when I graph this, it looks to me to be even, both ends go up. There's a little doop-de-doo in the middle, but it looks like it's got reflectional symmetry over the origin. So let me substitute my f of negative x here, or over the origin, over the y-axis. I'm sorry, it looks like it has reflectional symmetry over the y-axis, even that down, up, down section in the middle of the graph. So I'm going to substitute my negative x here. And I'm guessing that I'm probably writing underneath where I've got the Desmos section. So let me just make this smaller for a minute. And then you want to look at the negative x to the 6th power and the negative x to the 2nd power. And the thinking here is that substituting negative x in both of the places where you substitute negative x doesn't have any impact on the whole equation. There's no impact whatsoever. And so when you simplify that, you end up with f of negative x. The 5x to the 6th doesn't change. The minus 3x squared doesn't change. And none of it changes. And so this function is also an even function. Now when I graph letter D looks to me like it's neither. It looks like it might have some kind of symmetry, but definitely not about the origin or across the y-axis. So I am going to substitute my negative x here. Now, there are 3 places where I substituted negative x. Each one of them has an odd exponent. So each one of them is going to change the sign of the term. When I say the term, this becomes minus 7x to the 5th. This becomes minus 2x to the 3rd. This becomes plus 3x. But this guy doesn't change down here. And so this is definitely going to be a neither question. So f of, I'm going to try to keep this away from where I want to put Desmos. F of negative x equals negative 7x to the 5th minus 2x to the 3rd plus 3x, and then bring down that plus 1. And everything changed signs except the 1. And so this function is also going to be neither, or is also going to be nice. This function is neither even nor odd, which this is the first time we've seen that in this video. So neither. So for letter E, this graph also looks to me like it's neither. And so I am going to substitute my negative x, f of negative x. And there's 2 places to substitute it. It's going to look a little odd with the absolute value, but I'm basically going to just change both of those x's to negative x minus the absolute value of negative x. Now remember that the concept of even and odd is basically asking you, does that part of the function change sign or not? And so here, this term changed sign. That's not the tricky one. I want you to think about absolute value. Whether you start with x or negative x, your answer is going to be the same because it's going to be whatever the positive value of x is. And so this minus sign here does not change. So what I underlined in pink changes. What I've underlined in green, the absolute value part, doesn't change. And so your f of negative x ultimately gives you negative x minus absolute value of x, which is not what we started with, nor is it all negated. And so this is also going to be neither even nor odd. Last but not least, remember that I said that I'm not going to put any trig functions on your test, but I do expect you to be able to at least handle looking at them. And so I want to talk you through this one. When I graph it, this is a kind of a weird graph, but if you look at it closely, you can imagine that it would have rotational symmetry around the origin if you were to put your pencil on the origin and spin that graph around by 180 degrees, you should see that it would have rotational symmetry. So I am going to substitute negative x here, here, and here. And this is where you have to kind of remember, and this was on the formula sheet that we used in Unit 3, that sine of a negative angle is equal to negative sine of the angle. So that essentially is going to change the sign of this term. And so that term becomes minus sine of x. So f of negative x equals the negative x that we started with minus the sine of positive x, because this becomes this. So both terms change sign, positive, negative signs, because of the substitution of negative x. And remember that an odd function, like I said up above in letter A, when you substitute negative x, it changes the signs on all the terms and gives you the opposite of f of x. And so therefore, this function is also an odd function. I successfully paused the video before the clock went. Yay. So here we are at number 13. What I like to do when I'm looking at increasing, decreasing, and constant questions is I like to highlight before I start which sections are which, and it helps me focus on then what are the x values at the beginning and end of each section, because remember that the easiest mistake to make when you're writing the interval notation for increasing, decreasing, and constant is that you put y values instead of x values in the intervals, because your eyes are going up and down to look at the increasing and the decreasing, and then you forget to make sure that you're doing x values, which go sideways, not up and down. So I am going to use pink for decreasing and blue for increasing and orange for constant. So that's not a good orange. You're going to live with it. That's a constant interval, and this one down here is a constant interval. And then in here, this whole thing is decreasing. And then over here, this whole thing is increasing. And so when I do this problem, then I am going to look at the x values, and I'm going to say here that this is -3 to -1 This is -1 to ignore all these points. You don't need any of these. To +1, that's your decreasing. It's constant from +1 to +2, and it's increasing from +2 to +3. So the numbers that I underlined in red, or I can even highlight them in red, these are the numbers that are going to, it's too much highlighting. These are the numbers that are then going to be in your interval notation. So let's write that out. And your increasing interval is from 2 to 3. And remember that you'll always use round parentheses when you're writing increasing and decreasing. Your decreasing interval is from -1 to +1. And you have two constant intervals, and they are from -3 to -1. And you use the union symbol from +1 to +2. In letter B, I see increasing here and here. I see decreasing here, and I see no constant intervals. And so for my increasing, and remember that my x values are going to be the numbers that I use to represent them. And so my increasing intervals are from -2 to 0 and from 2 to 4. So -2 to 0, union 2 to 4. My decreasing intervals are from -4 to -2, union, and then from 0 to +2. And we said that there are no constant intervals, none, or NA, or null set. I know some of you really like making the null set. In this next graph, I see a decreasing interval here, I see an increasing interval here, and then that last interval is also decreasing. Now your x values are going to have some pi's in them. Again, don't worry, I'm not going to put something like that on your test. And there's really only two x values you have to worry about here because the rest of them are infinity. So it is increasing from -π/2 to +π/2. It's decreasing from -∞ to -π/2 union, and then from +π/2 to +∞. And it's constant nowhere, so there are no constant intervals. And by the way, letter C is the sine curve. For number 14, you need to show all of your work algebraically, and remember that we had said that if the directions say algebraically, then you need to show the work algebraically. You're welcome to check your answers on Desmos, and I'm not going to show you that here, but all you need to do to find zeros or x and y intercepts is graph the function and then literally just click on the x-axis or the y-axis. But also remember that you shouldn't have any decimals in your answers. And so there will be some fractions, and you need to show me algebraically how you got to those fractions. The other thing that you need to remember is that you should be able to factor. And for example, the case of letter A, you're going to need to use what's called the zero product property, which means that you've got a multiplication problem that is equal to 0. So you set each thing that's being multiplied equal to 0 and solve each of those pieces of the function. So for example, here, I'm going to start by changing f of x to 0, and I leave the rest of the function the way it is for my first step. And then I see that I can factor out a GCF of x. And so my next step will be to say 0 equals x times, and then 2x squared minus x minus 3. And now I see that what's inside the parentheses here, the 2x squared minus x minus 3, can be factored. And so I'm going to factor that. We've had many conversations in class about how, and so I'm not going to fuss at you right now about the different methods of factoring when there's a leading coefficient, meaning there's a number multiplied by the x squared. What I'm going to do right now is grouping, and so grouping says that I multiply the 2 times the negative 3, 2 times negative 3. The 2 is the leading coefficient, and the minus 3 is the last. And 2 times negative 3 is negative 6, and I want to look at negative 6 as a product and negative 1 as a sum, and two numbers that add to negative 1 and multiply to negative 6 are negative 3 and positive 2. And I'm going to put x's with those. And then I'm going to replace this middle term with minus 3x plus 2x. And so I'm going to rewrite everything inside the parentheses. I'm going to bring down the 2x squared. I'm going to say minus 3x plus 2x instead of this minus 1x, and then bring down the minus 3. Now I'm going to do grouping, which says look at two terms at a time. And I'm going to start with the first two terms and look for a GCF, and the GCF in those first two terms is x times 2x minus 3. And then the GCF in the next two terms is just 1. Now you really still want to write plus 1 because that becomes part of your answer. And then the 2x minus 3 doesn't change. You also want to check to be sure that looking for a different color, they don't exist, that the stuff inside of the parentheses is exactly the same signs and all, and then your GCFs, the x and the plus 1, are going to be part of or one of the binomials that you have in your answer. So kind of zooming back out again, I have to bring down the x that I factored out at the very beginning. So 0 equals, and then x times, and then my x plus 1, those are the GCFs that I underlined in blue, times 2x minus 3. So now I have a multiplication problem equal to 0, and I'm going to set each of those pieces equal to 0. And so do you see that we have three pieces? We have the x, and we have the x plus 1, and we have the 2x minus 3. And I'm going to take each of those three things and set them equal to 0. So x equals 0, x plus 1 equals 0, and 2x minus 3 equals 0. And then I'm going to solve each of them. So x equals 0, x equals negative 1, and over here 2x equals positive 3, so x equals 3 over 2. That has to be written as a fraction. I prefer 3 over 2 to 1.5, but if you give me 1 and 1/2 as a mixed number, I would accept that because it's not a decimal. So x equals 0, x equals negative 1, and x equals 3 over 2 are the three zeros of that polynomial equation. And if you graph the equation, you'll find that that's where the x-intercepts are. Now in this question, you're asked to find both the x and the y-intercepts. Remember that finding the x-intercepts and finding the zeros, notice, let's compare these two problems real quick. This question asks you, the first question asks you to find the zeros, and that's the same as finding x-intercepts. And so we're also going to find the y-intercepts here, so it just adds a piece to the instructions for this second problem. I see 4 terms, and if I give you something that's 4 terms, it's pretty much, if you think that you're going to need to factor it, it's going to be a grouping problem, and it will be factorable. I'm going to, again, to do my x-intercepts, let me start with that. I'm going to change colors just a little bit here. To find the x-intercepts, I'm going to change the f of x to 0. I'm going to copy the rest of the function as it is. And then remember that grouping says to look at 2 terms at a time. And so I'm going to take out a GCF. Here is x squared times x plus 3. And then the other thing that I want you to remember is that when you're grouping, your second GCF should always, always, always have the same sign as the middle term. So here, your second GCF has to be negative. And so I'm going to take a negative 9 out of negative 9x minus 27, and negative 9x divided by negative 9 is positive x. Negative 27 divided by negative 9 is plus 3. And the other thing that you want to check is that your x plus 3 is exactly the same inside both sets of parentheses. And so now you have 0 equals x squared minus 9. Those were your GCFs from here and here. X squared minus 9 times x plus 3. Remember that your x squared minus 9 can also be factored. So you end up with 0 equals x plus 3, x minus 3. And then bring down the x plus 3 over there. And just real quick, when I factored the x squared minus 9, I got x plus 3, x minus 3, in case you missed that. And so your zeros, or your x-intercepts here, are going to be x equals negative 3, and positive 3. And I would like you to list the negative 3's separately. You need to indicate that there are 3 zeros here, or 3 x-intercepts here. Even though on the graph the negative 3 would look like one x-intercept, I want you to write it twice, because it's a double root. Then I've asked you to find the y-intercepts, and so remember that to find the y-intercepts, you change all the x's to zeros. And so here my function is y. I changed the f of x to y equals, and that'll then just carry into my answer. And it was x cubed, so I'm going to write 0 cubed. And it was plus 3x squared, so I'm going to write plus 3 times 0 squared. And minus 9x is minus 9 times 0. And then minus 27. I know that it feels a little silly to have to write all that out when you probably know just by looking at the problem what the y-intercept is going to be. But in order to show this algebraically, I just want you to real quick write all of that out. But notice that the terms with the zeros, 0 to the third power is 0. 3 times 0 squared is 3 times 0, so that's 0. 9 times 0 is 0. So all 3 of these terms are just 0, and that whole thing ends up giving you y equals negative 27, which is your y-intercept. I do want to see everything written out that I've written in pink here. Same question here. I'm going to ask you to find the x and y intercepts. And so I will start with the x-intercepts, or the zeros. Change f of x to 0. Factor to solve this. So 2x is a GCF. That leaves me with x squared minus 4x minus 21. I would like to ask you to pause the video and just take 2 seconds and factor this before I do it so that you can make sure that you get what I get. And when you set each of those things equal to 0, and just real quick here, 2x equals 0 is just x equals 0. And I don't need this, you don't need to write out this part, but just keep in mind that thinking there. But then your answers for the x-intercepts are going to be x equals 0, positive 7, negative 3. And if you want to rewrite those numbers in numerical order, I don't care one way or the other for x-intercept and y-intercept and solutions problems. You can give me whatever order of answers you want. To find the y-intercepts, you write y equals and then change all the x's to zeros, and in this case everything has an x. 2x to the times 2x to the third is 2 times 0 to the third minus 8 times x squared, which is 8 times 0 squared, minus 42 times 0. Every term has a 0, so your y-intercept is 0. And remember that if you have an x-intercept of 0, that your y-intercept is also going to be 0. So that should make sense to you. Now, for number 15, you are asked to do both. Graph the function on Desmos, and I'm not going to even give you access to the calculators, so let's just get rid of that. So you're asked to both graph the function on Desmos and then algebraically. So on Desmos and algebraically. So I need to see the algebra. I need to see you write out the steps and then give your answer without decimals. And you know that each of these is going to be a decimal answer on Desmos, so you need to figure out how to find the answers using algebra and Desmos. What I hope to do between the time I'm actually sitting and making this video and the time that you get access to it is to actually superimpose a picture of or a screenshot of the Desmos graph into the answer key. And so, hang on one second. Turning pages. And so hopefully that's what you'll be seeing soon, even though I can't talk about it directly because I don't have it in front of me yet. So moving along, remember that algebraically you're still doing the same thing that you did immediately above. You're going to change f of x to 0, and then you're going to solve this equation. So here I would add 7 over x to both sides. So you have 7 over x equals 3. And then I would multiply both sides by x. The thinking is that if you multiply by x, then these x's over on the left would cancel, and you end up with 7 equals 3x, or x equals 7 over 3. And your Desmos graph should show that you have an x-intercept at 2.33333, and so that should verify 2.3 repeating is equivalent to 7 over 3. Letter B, again, changing the f of x to a 0. And you want to isolate the radical, and so I'm going to add 4 to both sides. So I end up with 4 is equal to 7x plus 5. And then I'm going to square both sides. And on the left, I end up with 16, and on the right, I end up just with what's inside the square root. And now you just have a linear function to solve, so I'll subtract 5 from both sides, divide both sides by 7. Yeah, you can't see why I just did that little jiggity jag at the bottom of the screen. I forgot you can't see my menus. So on Desmos, your x-intercept should show something like 1.5714 or some series of decimals that are similar to that. And that is what you would get for the fraction 11 over 7. So that should be verified there. And then thirdly, the rational function here. So the concept of multiplying both sides by the denominator so that 3x minus 2 times 0, so that over here then the denominators cancel, and over here everything is just equal to 0, so you end up with 0 equals just 13x plus 1. And that's linear, so just go ahead and solve that linear function, and you end up with x equals negative 1/13. And your decimal on Desmos, you might want to zoom in on Desmos. Now I can't remember because I've already made the Desmos screenshots, if I zoomed in a lot, but if you zoom in on the graph, I do remember that essentially what you're seeing on that graph looks a little bit like this. And I'm probably going to be redundant because I'm going to write what's probably already on your screen, but if you zoom in real close to the origin, you should see something that looks sort of kind of like this. And if you zoom way in on this, that should give you some very small negative decimal number, like 0.076 or whatever. And that is negative 1/13. And if you want to check it, you can use Desmos to say 1 divided by 13. And if you literally just go to an empty line in Desmos, type 1 divided by 13, and then look over to the right-hand side of what you typed, it gives you a little answer in a gray box. And so Desmos will give you answers to straight computations in addition to graphing. Now, for these three problems, you need to remember that the concept of absolute max and min means the highest or lowest on the whole graph. And that relative could be also called local. Those two words are very interchangeable in this context, and that means the highest or lowest point compared to those immediately next to. And I'm going to say here to those immediately on either side. Meaning that there has to be a right-left kind of a feel. You have to have points above a minimum in order to, points above a minimum on the right and on the left in order to actually have a relative or local min or max. And so there are going to be times when something looks like it's a high point, but if there's no points on either side of it, then you don't have a local or a relative min or max. So this first graph here, hopefully, I meant to do that in a different color. I meant to do the relative in green. Oh well. So in this first graph here, I tried to be fairly straightforward. So your absolute, meaning on the whole graph, the highest point is going to be that 1 point or 1,4, the point 1,4. And your absolute lowest point on the whole graph is that point down there, 5,1. Absolute highest, absolute lowest. Now, that 0.33, pretend like, I'm going to alter this for a second. Pretend like it's actually, I'm going to move that point right here. Pretend like it's there. It'll be easier for me to talk about if it's accurate. So the relative maximum here has it at 3,3 has points on the left and on the right. And so this point 3,3 is higher than the points on either side of it. Whereas this point does not have points on the left, therefore it's not a relative max. You can have a maximum point that is both relative max and local max, but in this case it's not. So your only answer for relative maximum here is going to be that point 3,3. And now I'll have the same conversation about the relative minimum. So if you look closely at where it says 2,2, that point has higher points both to the left and to the right of it. And so it is lower than all the points around it. Whereas this does not have any points to the right, and therefore it's not a relative min. So your answer to relative minimum is going to be 2,2. In letter B, when you're talking about your absolute maximum and your absolute minimum, let's start with the absolute minimum. Hopefully you see that this is the lowest point on the graph, and so that's going to be your absolute minimum. But when I'm looking at the maximum point on the graph, it's that 2,4, except that point is missing. And if you have an open circle where a max or min should be, then you don't have a max or a min. And it's not that, well, then 1.999 would be where the maximum is. It's just that there is no maximum. There is no absolute max. And so your answer here is going to be none or NA. And the same thing with the relative, there are no points. There's no point there that has lower points to the left and to the right. If 2, 4 were not an open circle, then it would be a relative maximum. But because the only thing missing is the point that you want to be the relative maximum, it isn't. And therefore, your answer here is also going to be none. Likewise with relative minimum, because neither this point nor this point meets all the criteria. This one doesn't have anything to the left. This one not only doesn't have anything to the right, but it's an open circle. Therefore, there's no relative minimum. And so I'm also going to write none for a relative minimum. And so the only thing in letter B that actually has an answer is absolute minimum. In this graph, we have a section that goes up to positive infinity. And if any part of a graph goes to positive or negative infinity, that is going to automatically cause you not to have an absolute min or max, whatever direction you're going. So in this case, this graph goes infinitely high. So there's no point that you can name that you can say this one point is higher than all other points. Infinity isn't a point. Infinity is a number bigger than any other number, and so you can't really use it as an answer to a finite question. And so the question, what's the absolutely highest point on the graph? There is none. What is the absolute lowest point on the graph? Well, that's going to clearly be that 0, 0. Your relative maximum, remember that our definition is it's got lower points on either side. We can't use the negative 1, 1 because it doesn't have any point that's lower to the left of it. But this point 2, 3 fits the criteria because it has points immediately lower than it, both to the left and to the right of it. And if you saw me doing these videos, you would see me pointing to the left and to the right with my hands in the air, but you can't see any of that. So the relative maximum in this case is going to be 2, 3. And then if you take a look at, there's 2 places where there's a relative minimum. And the relative minimum criteria are met in both of these places here, because at 0, 0 there are points immediately to the left and right that are higher, and at 3, 2 there are points immediately to the left and the right that are higher, and so these 2 points are relative minima. And you don't have to write union in this case. You can just write the word and or just put a comma, I don't care. But your relative minimum is going to be 0, 0 and 3, 2. So just real quick, silliness here. I'm saving all these videos to my desktop, and every time I go to, because I'm changing the names of the videos from the random numbers and letters to the problem numbers. So every time I go to change the name of the video, my screen or my wallpaper shuffles, and these are all pictures I've taken, and it just makes me want to have summer vacation and go driving somewhere. This particular picture is in South Dakota. It's called Badlands National Park. It's beautiful. It's a beautiful national park, and it's near Mount Rushmore. Near out west is not like near here. Near is like maybe 2 hours, and which in South Dakota 2 hours is like next door. Unlike actual next door, which is me knocking on my neighbor's wall in my kitchen. Anyway, I just have to tell you that on this very, 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 very cold Saturday that I'm making this video, it looks like I really want to go to that park right now. Anyway, let's graph some more Desmos. Thank you for listening to my commercial break. You can kind of see the little peeking out of the Badlands National Park in the bottom corner. And then you should go eat chocolate ice cream. So now I'm doing number 17, and I wanted to walk you through actually typing this problem into Desmos with the table of values, and then I will take a screenshot of how this problem looks in Desmos while I'm talking about it. So number 17 is a problem about the intermediate value theorem. You can surely do this problem without looking at table of values and just looking at the graph of it, but I really want you to understand numerically how the intermediate value theorem works, and so I'm going to actually be looking at all the numbers. So first of all, I'm going to start with the equation, but remember that when you want to get a table of values connected to a given equation, that you have to start by typing y1 equals. So you type your y and then type your 1. You have to give it a subscript. If you're using other equations, you can have one of them called y1, another one called y2, y3, y4, and you can make a table that has multiple columns with all your different y values, and I don't see us doing that for this unit, but just know that Desmos is flexible like that. So y1 equals, and then I'm going to type my divide sign to give myself a fraction, and then 3x plus 7 in the numerator and 3 minus x in the denominator. I'm going to zoom out just a little bit so that I can see pretty clearly the shape of the function and where the asymptotes might be. And then I am going to click in my next equation line, and I'm going to add a table. And the table is going to automatically give you x2 and y2. Not sure why they do that, but just go back and get rid of the subscript on the x and change the subscript on the y to 1, because what you want to do is, and it's just giving you this warning symbol because you haven't typed anything into the list yet. But what you're going to do is give it x values that you want Desmos to feed into the y1 equation so that Desmos can spit back to you the y1 values. And on the worksheet, the problem part A asks for x values -3 and -2, part B asks for +2 and +4, and part C asks for 0 and +1. So I want my table to go at least from -3 to +4. I'm going to do it -4 to +4 just for a little bit of evenness on both sides, because that's what my personality requires. So I'm going to start by typing -4. Then I'm going to down arrow or click in my next space -3. But once I have entered two numbers that establish a pattern, now I can press enter, 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 and that gives me more numbers in that pattern. And so now when I look at number 17, it's saying things like, show that the function has at least one zero on the interval -3 to -2. Well, I can zoom in and say, okay, yeah, my eyeballs see a 0 between -3 and -2. I can see that the value of the function at x equals -3 is negative, or it's below the axis, and the value of the function at x equals -2 is positive, or it's above the axis. And to get from below the axis to above the axis, it has to go through the x-axis, and that's a solution. But I can also look at the table and say, where x is -3, the y value is negative. Where x is -2, the y value is positive. And just because I started by looking at pictures and teasing myself with summary thoughts, I'm going to end with pictures. Oh, this is me driving in Colorado in the mountains. Sometimes I just take my car and put it on a mountain and don't look at a map and just drive. And this was clearly in the fall because the aspen were starting to turn golden. I highly recommend that trip too. Go see the golden aspen in Colorado someday. So hopefully you have just watched a video of me using this function here, the f of x for number 17, f of x equals 3x plus 7 over 3 minus x. Taking that function, making a graph of it, and also creating a table of values to go with it so that we can look at the signs on those values and then answer questions using the intermediate value theorem. And also, hopefully, there is somewhere on your screen, or will be very soon, a screenshot of that graph and that graph screen with the table of values on it, so that I can talk about it while you are looking at this. So remember that for the intermediate value theorem, and in this problem I stated it in the directions, but to kind of save space on your paper, I called it IVT. And you really want to use, and this should say using the intermediate value theorem, you really want to use the intermediate value theorem to answer these questions. And essentially the idea is that in order for there to be an x-intercept or a zero or a solution on a certain interval, you have to show that there's a point to the left and a point to the right of what you think is a zero where there's a sign change, where one is positive and one is negative. Remember that you cannot use this theorem to disprove that a solution exists, or to say no solution exists because they're both positive, because you can't use it to prove against. You can only use it to prove that one is for sure there, at least one, because it could be more than one. So anyway, using the intermediate value theorem, show that the given function has at least one zero on the interval -3 to -2. Remember that these values are always going to be x values, and so what you're looking at in your table is what's the value of f of -3 and what's the value of f of -2. Well, I see in the table that f of -3 is -0.333 repeating. That's negative, so I'm going to say, okay, f of -3 is negative. And f of -2 is 0.2. Well, that's a positive number, so f of -2 is positive. And since one is positive and one is negative, I have what we call a sign change. And if there's a sign change, then that means that on one side of a solution, the graph is negative. It has to cross through the x-axis in order to become positive. And so on the other side of this solution, the graph is positive. Therefore, there has to be at least one solution between -3 and -2. Done. Proven. In part B, it says, why can't we? And again, you want to look at the 2 and the 4 and say, okay, these are x values. And so I want to look at f of 2 and f of 4. and f of 2 is 13, so that's positive, and f of 4 is negative 19, that's negative, but wait, I'm even going to write that, but wait. F of 3 is undefined. There's an asymptote there. And if it says, why can't we? We're going to say it's not continuous. Because of the asymptote. And again, part C also says, why can't we? So I do want to start by looking at f of 0, whether it's positive or negative, f of 1, whether it's positive or negative. F of 0 is 2.3 repeating, so it's positive. F of 1 is 5, so it's positive. And so your answer here would be no sign change. So numbers 18 and 19 ask you to do function operations for whatever the given functions are. So in this case, f of x is 1 minus 3x, and g of x is at 5x cubed. Remember that the domain or any restrictions on domains for f of x and g of x could impact the restrictions on the domain of your answer function. And so keep in mind, it may just be all real numbers, and most of the answers for number 18 are, but in number 19 you really need to keep that in mind. So I'll bring that back again in number 19. In this case, excuse me, when I say that the answers, a lot of them are all real numbers, start with both f of x and g of x have a domain that's all real numbers, which means that I can input any value, any x value into f, the function f. I can say f of, and then any real number, any number that exists. And I can do the same thing with g. I can say the domain of g is all real numbers. I can input any number, any real number into the function g and get an answer. And so unless there is a reason why in my answer function I have to exclude a number from the domain, I should be free and clear to have all real numbers as the domains of my answers. So if I ask you to say f plus g of x, the first thing you want to do is say, well, I'm adding f of x plus g of x. And then substitute using the functions given for f and g. So f is 1 minus 3x, and g of x is 5x cubed. And then you want to simplify. Well, nothing here simplifies, and if your gut really tells you that you have to write this in standard form, that's fine. I'm not going to require it. But that's going to be your answer, and there's nothing in this answer that should be a domain restriction, and neither of the original functions have a domain restriction, so my domain is going to be all real numbers. In letter B, f minus g of x means f of x minus g of x. And so f of x is 1 minus 3x. g of x is minus 5x cubed. I should have given that to you in the other direction, g minus f, and then you would have had to distribute the negative. Watch out for that. That might just happen on your test. And again, if you want to rewrite it in standard form, that's fine with me. You don't have to, but it would look like this. Just don't mess up your signs. If you're going to rearrange the terms, make sure that you've got the right signs. And again, nothing about f, nothing about g, and nothing about my answer says there would be a domain restriction. And so I'm going to write that my domain is all real numbers. F times g of x is f of x times g of x, and f of x, and I'm going to use parentheses here because we're multiplying, so 1 minus 3x, and then times g of x is 5x cubed, and I need to take the 5x cubed and distribute it across the 1 minus 3x, so I get 5x cubed minus 15x to the 4th. And again, there's nothing in the original function f or the function g or my final answer that restricts the domain, and so my domain is all real numbers. And part D, f divided by g of x. Remember that g of x can't be equal to 0. And so that is going to impact our domain because there are places where the answer to g of x is 0, and that would restrict the domain for the answer of the division of the functions. So let's start with rewriting this as f of x over g of x, and then do the substitution. So that whole thing equals 1 minus 3x over 5x cubed. And there's nothing you can do to simplify that. So that's going to be my answer. But if you look at the denominator here, remember that your denominators can't be equal to 0. So your thinking here is that 5x cubed cannot equal 0, and therefore x cubed cannot equal 0, and therefore x cannot equal 0. So my domain then is going to be negative infinity to 0, not including 0 because 0 can't be in the domain, and going to positive infinity. Did I actually say but wait up there? Oh my word. Okay, so moving on to number 19. Number 19 is a little bit more problematic than was number 18 because of the fact that the function g of x has a restriction in the domain. So for no problem, A, B, C, or D, none of the answers, no matter what your answer looks like, your answer cannot have 0. So x cannot be 0. And since x cannot be 0 in one of the two functions, then x cannot be in the domain of f plus g, f minus g, f times g, f divided by g. 0 can't go into any of those resulting functions because 0 is not in play for the very beginning of the problem. So 0 is not a number that can be in any of our domains. So just keep in mind that your domain for all 4 of these, regardless of other restrictions, cannot have a 0 in it. So here we go. F plus g is f of x plus g of x. And so f is 2x squared minus 5, and g of x is 7 over 3x. And there is nothing that can be simplified there, so that is your answer. And you do see that there's an x in a denominator, so x cannot equal 0 here, and therefore your domain for the whole problem is negative infinity to 0, not including 0, and 0 to positive infinity. For f minus g of x, it will be very similar. I missed it. There's the clock. Darn it. I started making this video an hour ago and I waited the 45 seconds till the clock went off. F of x minus g of x, and so f of x is, yeah, you guys think I'm wacky. 2x squared minus 5, and then minus 7 over 3x. And again, there's nothing that can be simplified. Again, you've got an x in a denominator, and x can't equal 0 because that would make the denominator 0, and therefore my domain, again, is going to be negative infinity to 0 and 0 to positive infinity. In part C, f times g is f of x times g of x. F of x, I'm going to put in parentheses because we're multiplying. We've got 2x squared minus 5 times g of x, which is 7 over 3x. I'm going to rewrite this as a numerator, 7 times 2x squared minus 5 over the denominator 3x, and don't get lost there. All I did was I assumed that 2x squared minus 5 is over 1, and then I multiplied through the numerators and multiplied through the denominators. 7 times the parentheses, and then 1 times 3x. And so what you end up with there is 14 x squared minus 35 all over 3x. Nothing else simplifies. And again, you have an x in a denominator. X cannot equal 0. And so my domain here is, again, going to be negative infinity to 0, not including 0, 0 to positive infinity. And in this division, here's where the domain restriction really becomes obvious. In this final part of number 19, you want to do f of x over g of x. Simplifying this is going to have a little bit of a twist, but remember that g of x can't equal 0, and you have to consider the domain of the original function. So f of x is the 2x squared minus 5, and g of x is that 7 over 3x. And really what we're saying here is 2x squared minus 5. I'm going to write over 1 just so you can really see the division happen, divided by 7 over 3x. And if you're good with dividing fractions and you don't need to write this particular step right here, you don't have to write that step if you don't want to, but I would like to see the rest of it. So all of that becomes 2x squared minus 5 over 1 times, change division to multiplication, flip the second fraction, 3x over 7, and that whole thing becomes 3x times 2x squared minus 5 in parentheses because you're multiplying by the entire numerator, all over 7. Wait, there's more simplifying to go. And so if I distribute that 3 across the 2x squared minus 5, I end up with 6x cubed minus 15x all over 7. And I would accept that as an answer, although to be consistent, I normally would want you to divide it out. So you could write 6/7 x cubed minus 15/7 x. That's pretty ugly, but it's acceptable, and it would be more of a polynomial form. Now, here's the rub, the twist, the plot twist. Your answer here does not have an x in a denominator. So if all I said to you was, what's the domain of this? You would say all real numbers. But it can't be all real numbers for this problem, because where you got that from up here does not include 0. And so in your domain, your final domain here, you cannot include 0. So I went ahead and graphed these problems in Desmos ahead of time, and just included the graphs on the paper because I want to write on them, I want to draw on them. And so the question is asking, so let me back up a second. We're moving on to the concept of inverses. And one of the concepts that we've added in pre-calc is the question that you have to start with before you start computing the inverse of a function is whether or not there is actually an inverse. Because in Algebra 2, we were just having you compute all kinds of inverses, and we never really stopped to consider that some of these functions don't have an inverse that's also a function. And in order to do that, we talked a little bit about this when we talked about trig inverses, the sine or cosine, arcsine, arccos, arctangent, or sine with a little -1 as the exponent there that indicates inverse sine, inverse cosine. When we drew all those graphs and we reflected them over the line y equals x, we said some of the sine, cosine, tangent graphs are problematic because they don't pass the vertical line test. So your original function does pass the vertical line test, but your resulting function might not pass the vertical line test. And so what we want to do here for these functions that we're going to talk about in this case is say, look, if the original function doesn't pass a horizontal line test, then the inverse function isn't going to pass a vertical line test. And so, for example, in this first, and that's all you're answering, that's all you're answering for number 20 is, does it have an inverse function? Because it's 1-to-1. 1-to-1 means that the function passes both the vertical and the horizontal line tests. And so you can see in 20a that this function does not pass a horizontal line test, and therefore the entire function is not 1-to-1, and therefore no inverse function exists. Now, could you force the numbers exists? Could you force the numbers to compute an inverse function? Sure. You could type this sucker into Desmos in 2 seconds flat. If you wanted to, you would change all the x's to y's. You would say x equals -2y cubed plus 4y squared minus 3. And it would give you a graph that is a reflection of this, and it would not be a function. Well, in this context, we only care if the inverse is a function. And in this case, it's not. But in letter B, although there are asymptotes, and you can kind of see there, and the asymptotes are a little bit, well, they're definitely not whole numbers, but the horizontal asymptote is going to be 2/3, and we'll talk in Unit 7 about why, where I get the 2/3 from. But this is y equals 2/3. That's a horizontal asymptote. And then we have a vertical asymptote also at 2/3. And so what you'll see is that, yes, there is an inverse function because there's nowhere that this graph fails the horizontal line test. So I'm going to say, yes, let me zoom in up here. Yes, it's 1-to-1. An inverse function does exist. And then in this third example, hopefully you can see that it does not pass the horizontal line test. And if you could only see the mistakes I make, that was the least straight line I've ever drawn. So now with my new and improved straight line, you can see that it does not pass the horizontal line test. And although it's a nice graph and the original function is a function, the inverse would not be a function. And so we're going to say it's not 1-to-1. No inverse function exists. Having a few problems with the video for this last page, so I have been splicing pieces of it together. You're about to see number 21, but this is probably the third time I've shot it, so my apologies. What you're going to find is that I'm going to get to part C of 21 and splice in another video, and then I'll get to 22 part C and splice in another video, and hopefully what you see as a finished product will just be as if nothing happened with the videos. But in the meantime, you shouldn't hear the clock because the clock just went off, and I will talk through number 21, A and B, and then the other video will pick up number C, or letter C. So here we have, the question is asking you for each to find f of g. So you need to find f of g, and you need to state the domain of the resulting function. And so what I like to do here is start with rewrite it, because this notation, that's a little weird. In fact, let me just make sure that you all understand that there's a difference. F times g of x means multiply, which is very different than f of g, which means compose. So that's composition. And that's when you take g, the function g, and you use it as the input for x, or for f, the input for function f. And that's a very different concept, whereas in the multiplication, you've got two functions that are acting the same and that are being multiplied to each other, and the factors are commutative. The process of multiplication is commutative, whereas in composition, it's not commutative. You can't go back and forth, and G is put into X. So anyway, I'm going to take this function G, and I'm going to put it where the X is in function F. And so this first problem is fairly straightforward. I like to start by writing F of G of X equals, and then I'm going to take that G of X and make it the denominator with 5 in the numerator. And that whole thing just becomes 5 over negative 3x squared. That cannot be simplified. You'll need to simplify anything that can be simplified, but in this problem, it cannot be simplified. And then you need to consider, although this original function has no restrictions on the domain, this function cannot have x equal to 0. And the same with your resulting function, x cannot equal 0. And so you are asked to give the domain, and the domain here is everything except 0. So negative infinity to 0, not including 0, and then 0 to positive infinity. And then in letter B, I'm going to do the same thing. I am going to take the function G, and I am going to use it as the input wherever there's an X in function F. And like I said, I like to start by writing F of G of X in that notation. And then I'm going to take 7 times, and then G is radical 4 minus X, that's squared, minus, and then the radical 4 minus X again, so that this and this are the G of X, and that's where you squared it and subtracted it. Now remember that a square root squared is just what's inside the square root. So that whole thing ends up giving you 7 times 4 minus x. But you can't simplify this radical over here. And so I'm going to distribute the 7. So now I have 28 minus 7x minus radical 4 minus x. That can't be simplified any farther. But both the function g here and the function that is the resulting composition or composed function have this radical 4 minus x. And so here's where I'm going to say, okay, I'm going to think to myself, remember that what's inside a square root, 4 minus x, has to be greater than or equal to 0. And so 4 has to be greater than or equal to 0. And so my domain of the composed function, or of my answer, has to be all numbers x. My apologies. I am going to go back and fix that. Not 4 is greater than or equal to 0. 4 is greater than or equal to x. Because in order to get the domain, you need to think 4 is bigger than whatever x is. And therefore, you want the domain to go from negative infinity to positive 4, including the 4. Now, I'm going to zoom out on A and B here. In the rest of the video, I'm not going to really be able to zoom out just on number 21. So get written down what you need to for number 21 here. because when I go forward, I'm not going to have this same screen. I need to redo a piece of the video, and I forgot what colors I was using. So if my colors are off, I'm sorry. Anyway, to finish up number 21, letter C, we are going to substitute g of x into the places where there are x's in the function f. And so I'm going to start by writing f of g of x. And then that g is going to be where I circled yellow up there. And so that is going to equal 5 times 2x plus 1 minus 3 times 2x plus 1 squared. And again, this is where I substituted the g of x. Now, in order to simplify this, what I would do is I would take, I would start with just this binomial, and really squaring a binomial means that you're multiplying by itself. And to me, that means that I need to FOIL here, and that's exactly what I would do first. And you may want to stop the video and FOIL it just to make sure that you can, rather than just randomly copying my answer. But when you've FOILed this, you should get 4x squared plus 4x plus 1. So just pause a second and make sure that you understand where those numbers come from. And then I'm going to replace that parentheses with the 4x squared plus 4x plus 1 and not have the exponent up there. So this whole thing becomes 5 times 2x plus 1 minus 3 times 4x squared plus 4x plus 1. And then I'm going to distribute both the 5 and the minus 3 in the same step. And so here I have 10x plus 5, and then I have minus 12x squared minus 12x minus 3. And then when I look at combining like terms, only the 10x and the minus 12x are, oh, that's not true. 10x and minus 12x are like terms, and then the 5 and the minus 3 are like terms. And so I am going to pull that minus 12x squared up front. 10x minus 12x is minus 2x, and 5 minus 3 is plus 2. Now, because neither of the original functions, f or g, have any restrictions on the domain, and your answer wouldn't have any restrictions on the domain, then your domain is just going to be all real numbers. Remember that I lost a little piece of the video, so if you want to see A and B again, you're going to need to rewind because I can't zoom out because I don't have them here. I will move on to number 22. So 22 part A, didn't lose the video, I just need to splice some things in. Anyway, you'll see the whole video, I just can't zoom out. So there. Hopefully what I'm going to do is put a picture of the graph inside of the picture of this video, so that I can look at whether the graphs are one-to-one. And I just want to point out that where it says here to decide if the function has an inverse function. And the key is everything's going to have an inverse. It's just whether the inverse is a function or not. And so you really want to ask yourself, if it has an inverse function, then it's 1-to-1. So let's say we're going to ask ourselves the question, is it 1-to-1? Meaning, does it pass the horizontal line test? That was some kind of fancy question mark there. And just FYI, that was the same as question number 20. Probably should have put 20 and 21 in the opposite order, but it's way too late now. So in letter A, I'm going to try to have a graph up in the corner of this so that you can decide for yourself whether it's 1-to-1. And you should be able to see that the graph is a quadratic or a parabola that opens down, and it's definitely not going to pass the horizontal line test, so it's not 1-to-1. And so what you want to say here is that the graph is not 1-to-1. That's your reason why. And then the answer is no inverse function. It's not 1-to-1, therefore there is no inverse function. Now in letter B, again, I'm going to try to have that graph in the corner of the video here, and you should be able to see from the graph that the function is 1-to-1, which means it does pass the horizontal line test, and therefore there will be a inverse function. And so what I'm going to do here is change to compute an inverse function. Remember that you change your f of x to y, leave everything else the same. And then wherever there's a y, write an x, and wherever there's an x, write a y, and that's going to give you the inverse function. And then you want to get the y by itself. So in this case, in order to get the y outside of the square root, you want to square both sides. And I end up with x squared equals, and then it's just whatever was inside the radical, so 2y minus 5. And then I am going to add 5 to both sides, so I get x squared plus 5 equals 2y. And then I'm going to divide both sides by 2, so I get x squared plus 5 all over 2 equals y. And I really prefer, I wouldn't take off points for that, but I really prefer that you write this with coefficients. It will help you when we get into polynomials. So 1/2 x squared plus 5/2. And then remember that you want to rewrite that in function notation, which means that you're going to use the f inverse of x notation. And so you will write this with the f minus 1 of x equals 1/2 x squared plus 5/2. And that's your function inverse. The question also asks you to give the domain of the function. Get that out of the way. And remember that if you are only looking at this as a function and not considering where it comes from, you would think that the domain is all real numbers. But here's where you really need to consider the domain of the original function here. And when you look at the graph up in the corner of your screen, you'll see that the range, remember that the range of the original function becomes the domain of the inverse function. And so here, the range of the original function is 0 to infinity. So the range of the original function is 0 to infinity. Take a look at the graph and make sure that you see that the range of that function, the square root function, is 0 to infinity. And then that becomes the domain of the inverse function, and the domain of this inverse is the same, 0 to positive infinity. Now at this point I should be able to pick up on the video that I made a few days ago, but when I zoom out again, at some point the colors are going to be different and the layout of each problem is going to be a little bit different for just these three problems. But anyway, that's letter B. Well, I talked through problem C. It was great. It was inspiring. It was so brilliant. And then the app crashed and I lost just C. So the rest of the video was saved up through number 22B. So let's finish up here. Letter C. And again, hopefully you're looking at a graph of both y equals 4 over 7 minus x, as well as x equals 4 over 7 minus y. Okay. And in order to get the y by itself, you're going to want to multiply both sides of the equation by the denominator. That has never happened with this app before. This app usually behaves itself. Oh well. So I'm multiplying both sides by the denominator so that on the right-hand side, the denominators cancel. And so now I just have, I'm going to go up to the top here, the 7 minus y times the x, and all of that equal to 4. And then I'm going to distribute the x. So now I have 7x minus xy equals 4. And you want to rearrange the equation so that you have xy by itself. Your rearranged equation may end up looking different than mine. I'm going to subtract 4 and add xy to both sides so that my xy is positive. You might end up with 4 minus 7x equals negative xy, and then all your signs are just going to be opposite mine, and you're still going to be right. But the next thing that I want to do is divide both sides by x. And so over here, that's going to look like 7x minus 4 all over x equals y. And then you want to rewrite your answer in function notation. Take a look real quick at the steps. Make sure you understand how I got to y equals 7x minus 4 over x. And then rewriting this in function notation, I get f inverse of x equals 7x minus 4 over x. Remember that you are being asked to find the domain for each of these problems if a function inverse exists. And so here, because you've got an x by itself in the denominator, x cannot equal 0, and therefore your domain will be negative infinity to 0, not including 0, and then 0 to positive infinity. And then last but not least, I've got this f of x equals x plus 1 over this absolute value of 5 minus x. And hopefully you're also seeing a graph of this on the other side of the screen. And if you look at this graph, you will see that it is not 1-to-1. And so that is going to be your answer, that it's not 1-to-1. Therefore, no inverse function exists. And remember that this is a good example of a question that if I put this on the test and say, find the inverse of this function if one exists, and you don't know how to do the algebra for it, and you have forgotten to look at whether it passes the horizontal line test as your first step, and you're sitting there frustrated because you don't know what to do, and you raise your hand and you say, Miss, hey, I don't know how to substitute switch the x and the y and solve for y when it's inside an absolute value, and you can get all frustrated, and then you ask me a question, and I'm going to say, That's it. That's all I'm going to say. So be careful that you use the horizontal line test first to see if a function exists, and if it does, then find the inverse and give the domain. Now, remember that the inverse problems that I give you that say, and the directions will be a lot like this. Using compositions, prove that f and g are inverse functions. Remember that how I'm giving this to you, the way the wording works, is that you're proving it. You're basically showing algebraically, you're verifying, which means that they are inverse functions. I'm telling you f and g are inverse functions. It's not a yes or no question. I'm not saying to you, are f and g inverse functions? And if so, show why. I'm saying f and g are inverse functions, and you are going to use composition to prove that, or to verify that they are inverse functions. And the way you do that is you show both f of g of x is equal to x, and you have to do both, and g of f of x is equal to x. And so here I am going to compose f of g of x, and in this case I am going to take this fraction and substitute it in these two spaces for x. It's going to look a little crazy at first, but remember, because they are inverse functions, stuff is going to cancel all over the place very quickly. These problems won't take a lot of steps. They're just going to have a couple ugly fractions at the beginning. So here, f of g of x, I'm going to substitute that fraction g 3 times, and then negative 2x over x minus 3 in the numerator. And then the denominator of the function f is x plus 2. So I'm going to take that same g of x here, and I'm going to start with that. So in the denominator, negative 2x over x minus 3, and that whole thing plus 2. So that I have substituted g of x where the x's are in the original f function. And now I'm going to simplify both the numerator and denominator of this big ugly fraction. So I'm going to start with the numerator, and I'm going to multiply 3 times negative 2x, and I get negative 6x over x minus 3. And then I'm going to take the 2. I want common denominators, and so I'm going to multiply by x minus 3 over x minus 3. so that I have negative 2x plus 2 times x minus 3 all over x minus 3. And if I were you, I would stop the video for a second real quick there, pause it, look at that combination of functions, and make sure that all makes sense to you. And just in case you want to see colored coded, this denominator here becomes this here, and the green became this here. All right. Then I'm going to take that fraction and the denominator. Well, first of all, do you see that both the numerator and denominator are now a single fraction? They're ugly, but they're a single fraction, and they have the same denominators. Therefore, I can cancel the denominator. So I'm going to take that whole thing and rewrite it as just negative 6x over. Now I'm going to go ahead and simplify this row right here, the negative 2x plus 2 times the parentheses. So I get negative 2x plus, and then 2 times x minus 6. And now I have minus 2x and plus 2x, so that whole thing cancels. And I get negative 6x over negative 6, and the negative 6's cancel, and that whole thing equals x. Oh, and I suddenly realized that I ran out of room to do g of f of x. Well, so my f of g of x checks, and I'm going to create a space and make myself stay in that space. Now I have to do g of f of x. I know you guys just sit and laugh while I'm talking to myself about making the video in the video. So g of f of x, I'm going to go back and erase the scribbles that I made on the functions, and I'm going to switch over colors, and I'm going to say this time I'm taking the function f here, and I'm going to substitute it into the x's in g. And so that is going to look like this. Negative 2 times 3x over x plus 2 all over, and then f again is 3x over x plus 2, and then minus 3. So what I did there was I put the function f of x here and here. And now I need to simplify all of that. And so I get negative 6x over x plus 2. Oh, that already feels familiar, doesn't it? And then for the denominator, I'm going to multiply this by x plus 2 over x plus 2 so that I can have that common denominator of x plus 2. So now I have 3x minus 3 times x plus 2 all over x plus 2. How am I doing on space? I'm doing all right. And then I can cancel the denominators there, and that whole thing ends up as just negative 6x over, and then I'm going to simplify this right here over 3x minus 3x minus 6. Please notice that the 3x minus 3x is 0, so you get equals negative 6x over negative 6. That whole thing equals x. And so now both f of x, or f of g and g of f equal x. And remember that that's what you need to show in order to verify that these two functions are inverses of each other. So for letter B here, I again want to prove that f of g is equal to x and g of f is equal to x. So I am going to start with f of g of x. Hopefully I will use my space wisely. And so I'm going to take this huge cube root and I'm going to put it here where it's x cubed. Aha! So that already sounds like a deal. So 6 minus 2 times, and I'm going to put parentheses there, cube root, big ugly stuff inside of the cube root, 6 minus x over 2, parentheses, and then cubed. Now, when I cube this whole thing here, when I cube this, that gives me just the, because it's a cube root cubed, that gives me just what's inside of the parenthesis, or the inside of the cube root. And so that whole thing ends up being equal to 6 minus 2 times the fraction 6 minus x over 2. Now, be careful. I see that my 2's cancel, but the minus sign does not cancel. And so really what I have here is 6 minus parentheses 6 minus x. I really need you to understand that that minus sign stays and the parentheses stay because you have to distribute that negative as a -1 across both of the terms that were in the numerator of the fraction. And so now this whole thing equals 6 minus 6 plus x, and all of that equals x, which is what we were looking for. Boom. That's f of g of x. And then I wanted to do g of f of x. And this time I am going to take the expression, hang on while I get rid of all the highlighty stuff. I'm going to take the expression 6 minus 2x cubed and put it where the x is in the numerator of that big ugly fraction inside of that big ugly cube root, but watch everything cancel real fast. So that ends up becoming big ugly cube root, big ugly numerator 6 minus, but then the function f is 6 minus 2x cubed. It's going to get uglier before it gets prettier, all over 2. And then I'm going to distribute the -1. So work inside the cube root first. You still have to write, yes, you still have to write the cube root. Equals cube root of numerator 6 minus 6. There goes the clock again. Do you know how long I've been working on this video? 6 minus 6 plus 2x cubed over 2. Yes, you still need to write the cube root. Oh, are you wondering if you still need to write the cube root? Yes, you still need to write the cube root. And then the 6's, 6 minus 6 is just 0. So that whole thing really fast starts boiling down to 2x cubed over 2. Now my 2's cancel, and all of that is equal to the cube root of x cubed. I can safely say that's the last time you're going to hear that clock in this one video anyway. Equals x, because we're so close to the end. So both f of g equals x and g of f equals x, and so both of those functions equal x. Therefore, you have verified that f and g are inverse functions. I would say for letter B here, I have intentionally included some simplifying skills that have been problematic for students at your level of pre-calc and probably shouldn't be. Distributing the negatives and knowing when to drop the radical and when to divide and when not to divide. So I want you to really pause the video here. If anything went against what you thought it was going to be, I want you to look real closely at the simplifying steps and make sure that every single one of those steps makes sense to you. And I am going to grade your work very carefully, step by step for this. So last but not least, you want to use the graph given to graph an inverse. And so here, I am going to look for places where the original function crosses easy points. Because remember that graphing an inverse is basically just exchanging x and y values. And so here I see that I have the point 0, -1, and 1, -2, and I have the point, sorry, got distracted, 3, 2 here, and 4, 1 here. And then what I want to do is graph each of these ordered pairs reversed. So I'm going to reverse the x and y. So I'm going to graph -1, 0, -2, 1. I'm going to graph the point 2, 3 and the point 1, 4. And it might not be obvious to you what direction the curve of the rational functions go. That's a little tricky. But in this case, you had asymptotes at y equals 0 and x equals, it's probably x equals 2. And so I'm going to change those asymptotes, and I'm going to make them at, instead, x equals 0 and y equals 2. And so my inverse function here is going to, my iPad just fell off of its stand. My inverse function is in red, and it's going to go through those points and follow those asymptotes, and it's going to look something like this. And the other thing that I would like for you to do is also graph. So really here, by the way, you're just looking at the original function that I gave you, and let me see if I can trace this accurately, and the red function that I just drew that is your answer, and the red is just your answer, that's it. But I would also like for you to show me the line y equals x, and the line y equals x just goes through 0, 1, 1, 2, 2, 3, 3, all the points where x is equal to y, and just draw that with a straight edge, please. I can't on my iPad, but there's your y equals x. And then just kind of check to see if the red and the blue look like they are, if you can ignore all my pink and light blue scribbles, to check this, that the red and the blue graphs are reflections of each other over that line y equals x. Now, in this other graph, I should have put this first because it's a little bit more straightforward. So here, remember that the way my graphing software doesn't do square root functions as far as they should go. So this is actually a point right here. And that point is a good point to use as a base for the inverse function. So the endpoint of my original function graph is -2, 1. And so my endpoint for the inverse function graph is going to be 1, -2. But I also see that this point, or this graph, goes through easy to graph points at these places. So this is -1, 2, and over here, this is 2, 3, and this point over here is, hang on, I can't see, 7, 4. And so I'm going to literally graph those 4 points. And so I'm going to graph 1, -2. That's going to be my endpoint. And then 2, -1. And then 3, 2. and I can't graph 4,7. It would be up here somewhere, and that just gives me some direction to go in. And so my inverse graph is going to be something like that. And then I just ask you to also graph y equals x, which will come like this, there, and label it y equals x. And that proves to me you understand what functions are, or inverse functions are. And there you have it. My apologies again for the length of this video. Hopefully that it's useful to you, and hopefully you were able to skip over the things you didn't need, and that you found helpful the other things, especially the Desmos segments. And I hope that you have a chance to just get some good rest and eat a good breakfast on the day of your test, and I will see you soon. Bye.